Alright, hell yeah. We got Irodov, problems in general physics, and this is problem 1.184. This was a viewer request, you know what I mean? Can I just do my thing, you know what I mean? So that's what we're going to do. And even I'm just going to learn right off the bat, because we have, like, we always got to start where I always start with F equals ma. And I didn't realize this, that, you know what I mean, when you have an equation, sometimes you have like a proportionality constant, like right here. Well, this is basically that. It's basically saying that force is proportional to motion. You know what I mean? Hey, we have a force over here, and we're experiencing some sort of motion. Now, this is a special type of motion. It's going to be a change in velocity. You know what I mean? So, given a change in time. So that's the definition of acceleration, is change in velocity, change in time. You can also write it as dv dt. Okay, hell yeah. But now what we're saying is just like, yeah, so force is proportional, force is equal to acceleration, and then multiplied by some sort of constant, multiplied by a constant, and that constant just happens to be mass. You know what I mean? So if the constant wasn't mass, just for a second, you know what I mean, and we said that, hey, I am observing this mass, and then it's on like a flat, frictionless, icy lake, and I want to apply a force to it. And then I want to know, the question is like, hey, what's its acceleration? What's going to be its change in velocity every second? You know what I mean? I want that value for acceleration. Now, it could have happened where force is just equal to acceleration. You know what I mean? If you put 10 newtons on, we could have just said, hey, you get you get a change in velocity of 10 meters per second every 1 second. You know what I mean? And this is cool because there's no reason why it couldn't have been this way. You know what I mean? Just with where mass wasn't really necessary, it wasn't a function of mass. You know what I mean? So if you had a larger mass, hell no, that thing ain't moving. But if you have a lighter mass, no, we can get that thing up to speed. You know what I mean? So I'm just showing you, how to read equations. Because if you do have an equation that's like this, okay, well, hell yeah, it's a direct correlation. And I guess in this scenario, you're still like, you would still be talking about putting a force on a mass. It's just that mass is not part of the equation. Like, obviously, this is not what we see. But I just wanted to bring that up. Especially because, if you're analyzing something that has mass, usually the mass doesn't change unless it's like a rocket and it's like losing chunks of mass, and it's, and you're putting the same amount of force with less mass. Hell yeah, you're gonna, stuff like that. But okay, so but we do have F equals ma, and if we identify a force, you know what I mean. So that's this like the textbook side. You know what I mean? And in our case, hell yeah, we got gravity underneath. I mean, we got the Earth underneath us. The center of the Earth, hell yeah. And then you have little chunks of mass. The chain has mass. So sweet. And so we have identified that we have mass. We have identified that this mass of the chain and the mass of the Earth, there's going to be a force between them. That's going to be the force of gravity. So this is, I would always start here. Gravitational constant, mass of the chain, mass of the Earth divided by the radius of the Earth squared. But you don't have to get too carried away, because all these three terms, these just equal to 10 or 9.8. You know what I mean? 9.81. Gravity. So we can say the force of gravity is mg. Now, I'll say this a lot, is just like, because sometimes using the F equals ma equation isn't super intuitive. It looks like we have something that probably goes in that side. Well, no. So when I do F equals ma, I write F equals ma. I want to dot out the mass that I'm actually analyzing, so that's going to be like the whole chain. You know what I mean? And it might be parts of the chain. We'll see in a second. But now, we have the part that we're analyzing, the mass, and now we want to know its acceleration. And we want to know if there's any forces on it. So sweet. So that's exactly what we're going to do. And we're going to try to make the problem simpler and see if we can come to some sort of conclusions. Okay, hell yeah. So in this case, you know what I mean, force of gravity goes in here, and so you get force of gravity is equal to mass times acceleration. You get mg is equal to ma. And if you were interested, you know, in trying to find the acceleration, well, hell yeah, you would solve for the acceleration. So g is equal to the acceleration, or you would rewrite it that the acceleration is equal to gravity. What do they call this? Acceleration of gravity. Hell yeah. So yeah, and so this is for just an object in free fall. You know what I mean? We don't have any forces except one, and that's the force of gravity. Sweet. So now we have to kind of analyze what we have here. You know what I mean? So what I'm going to do is kind of simplify the problem for us. Let's just take down a string, and right before we hit the ground, let's put a big mass. And we're going to say this mass is equal to, so that mass is equal to, and we're going to say this chain, the mass total of the chain is mt. That's going to be the mass total of chain. I mean, just so we can say, hey, I'm going to put all the mass right before we impact the ground. I don't know, just for a scenario, just you know, to start out with. And I'm going to say, well, this isn't the mass total. You know what I mean? Maybe, because we have we have oh yeah, mass total, and then we have length total. And I guess I'm just going to call that, I mean, I guess they just call it L. So we have L. Yep. So yeah, they call this L. You know what I mean? I might call it L naught. And this is the total length of the chain. Alright, hell yeah, I'm back, and we definitely took a long break, so, and that's good, because I was just thinking, I want to slow roll this problem. So we had to identify what the total length is. I'm just going to say that's L naught. But now we have to, you know what I mean, hey, what's, and this is the height. We have to have this as some sort of length. I was going to call it length horizontal, but that might be confusing. But I don't know. Length horizontal, there you go. So we're going to do that. So LH is horizontal length. And now we have an equation that the length total, L naught, is equal to the horizontal length plus the height H. Alright, hell yeah. And then the mass of the chain is related to the total length. And so we can say, what's the mass of this portion of the chain? Well, it's going to be the ratio of this portion divided by the total length. So we're going to say, and I'm going to call this mass B, and then we'll call this, the remaining portion of the chain, mass A. So there you go. So we got mass B and mass A. So I'm going to say mass B is equal to, well, that ratio. So we have height divided by the total length, or L naught, times the mass total. Cool. And yeah, I like those subscripts. Hell yeah. And then, so the mass of A is going to be L horizontal, the horizontal length, L naught, and then times the mass total. Alright, so right here we just kind of really want to figure out what's going on. So what I'm going to do is we're going to attach this to a ceiling and then just have the mass of B, the hanging part of the chain, and just to see what's going on. So then what we do is we dash this out and do a free body diagram. What a free body diagram, from my perspective, is we're going to take this and then put it into the deepest reaches of space and just set it there. And then we're going to analyze it. And we're definitely going to analyze this scenario. In this scenario, this thing is not moving. You know what I mean? Zero velocity at time 0 and 0 velocity at any time. You know what I mean? So just a hanging mass from a ceiling is not moving. I think we all agree with that. But then, in this scenario, we still have an Earth underneath us. So we know from that F equals ma perspective, cool, we don't see motion. So I always write F equals ma, and then I throw eyeballs on this side and be like, well, do we see motion? In this case, no. You know what I mean? So our acceleration is 0. But then we go over here to our textbooks, and is there still known forces on this mass? And we do say yes. We have the force of gravity. You know what I mean? G, M, M-E, radius of the Earth squared. So that's on this side. Or we just said that's just the mass mg. You know what I mean? Because these three portions are g. Okay, hell yeah. So we know that even if this thing is in deep space, we know it's not moving, but we have just identified one force on it. So if we take this math and throw it as far away from all the stars as possible, and we're still going to say, hey, there's a force on it called the force of gravity, mg. So now what? You know what I mean? Well, in this scenario, we're going to say that this should be moving. You know what I mean? Because we have F equals ma. What this says is that if we identify a mass and we identify that there's a force on a mass in a particular direction, well, you're going to have acceleration in that direction. You know what I mean? If this is velocity 0, you're going to have a change in velocity, and it's going to keep on speeding up. But that's what we don't observe. So now this is a fundamental property of free body diagrams, and I think it's Newton's second law, is that or whatever. So if we observe that this is not moving, the only way to make sure this is not moving is to put an equal and opposite force on it that's equal to the force of gravity. And in this case, that's our tension. You know what I mean? So let's draw this thing one more time, and we know that, hey, we have a tension member this way, and then we have a this is the force of gravity. This is mg. So that's kind of another way to do it. I'm just going to say the tension is right here, but right there is just more visually obvious that the tension is pulling up this way as much as the mass is pulling down. So those, and this is super basic, but it's just very important, because if you don't have this totally spelled out for you and you do more complicated problems, but you can't just remember, because your teachers will speed through these basic principles and just assume that you know them down, you know what I mean, pat, but it's like, hell no. So here we go. So we see that these are equal and opposite. So now we have and again, what the hell does this say? This says the forces in the y direction are equal to the mass times the acceleration in the y. We know the acceleration is 0, so now we have the sum of the forces in the y direction is equal to 0. We sum the forces in the y, we have a t up minus mg down, and that's equal to 0. Therefore, t is equal to mg. So now we have the tension in the cord is just equal to the mass of b times the gravity. So let's write that. The tension in the cord is equal to the mass of B times gravity. Hell yeah. And tension is also a force. You know what I mean? You could also write this as just like, hey, force of tension. Sometimes that might be better for your learning ability. If you can identify on a force on this side, label it F, and then put a subscript of what it is. Gravitation, force, tension, you know what I mean? Maybe an electrical force. Anyway, so hell yeah. Okay, so now Yeah. So now we have something going on, because let's do the next scenario. Is now we just have this mg, and the mass of the bottom part of the chain, mb. So we're gonna have this as mb, and we're gonna say mb jumped off a cliff. You know what I mean? Hey, it still has a force on it. Force of gravity is mbg. And there is no other force. So if we go F equals ma, hell yeah, the force goes in this side. So we have mbg is equal to that mass that we're analyzing, and that's mass of b times the acceleration. So those cancel because of the equation, and then we have acceleration is gravity. So there you go. And so in this case, we're going to have a change in velocity of 10 meters per second for every 1 second. Okay, cool. But we know that's not the case for this problem, because we're not just in free fall. We are, well, let's set up one example. So we have a pulley here, and then we have another mass right here. So this is going to be the mass at A, and now we have the mass at B. We'll just write it a little bit bigger. So cool. So now what? You know what I mean? So this problem is essentially a pulley problem. And then just to spell it out, the only difference between a pulley problem like this and this problem is my mass at A is going to get smaller. So if I have a change in velocity, let's say the velocity is 0 because I'm holding this, and then a second later it has some sort of velocity at 1 second. Well, then I know the average velocity is going to be, the midpoint between those. So it's going to be velocity at 1 second. It's going to be 1/2 that. And then if I know the average velocity, I know the distance, because I know I just traveled in 1 second. And so I know the distance is going to be, or the distance traveled is the average velocity times time. And time is 1 second. So basically I know the distance is going to be 1/2 V1 times 1 second. You know what I mean? Units will cancel, and now I know the distance. So hell yeah. But when that distance goes this direction, you know what I mean, in our problem, like let's say at 1 second, now this chain is over here. Okay, so this length got reduced. So now my mass of A naught is greater than my mass of A at time is equal to 1 second. So that's the problem we're going to do. And then when the chain is almost over here, there's literally almost no mass left, but you still have a huge force on a small mass. So that's the other part of the problem visually, is we want to say, whoa, you know what I mean, mass of B is real big, but we get to the scenario where maybe mass at A, right at the very end, is, and I'll do the pulley out here, sorry about that. But yeah, the mass at A is really small. So in this, just visually, you know what I mean? And let's say you didn't know about the equilibrium, and we just said, hey, let's do two scenarios, is that the tension in the string just is almost proportional, or just equal. The tension in the string is equal to mbg. I think we just showed that this example, that was going to be the tension in the string. Obviously, so that's gonna be our force of tension that's going to drive this little thing. And it's not quite, because you do have an equilibrium with pulley problems. You'd have to do one of them to kind of see that. I can't actually spell out exactly what's going on. But if this is super tiny and this is super big, hell yeah, you can just say, sure, let's just say the tension is going to be mbg, and that's going to be the tension on that little mass. So then we go to our F equals ma equation, and we say, hey, well, we want to find the acceleration of mass at A, and we already know the force on it. It's going to be that force of tension that we already found. So we say mbg is equal to maa, and then we can say, what's the acceleration of this mass A? So the acceleration of mass A is mb divided by ma times g. You know what I mean? So hey, gravity was 10, but now we're saying that it's a ratio between, hey, look at this, like this might be 10 times the mass at A. And if that's the case, if this is 10 and this is 1, then my acceleration at this point of this mass is 100. It's 100 meters per second, you know what I mean? And the second, like, there's almost just no mass right here because the chain is just off. Hey, this literally goes to infinity. We're going to have acceleration as infinity. But, you know what I mean, that's probably, who cares? You know what I mean, because a second before that, the acceleration is some hella normal number. Still big, but still, you know what I mean, like 100 meters per second. You know what I mean? So, You're not going to get an infinite velocity just because the acceleration will be infinite when there's hardly no mass around that corner. Okay, hell yeah. And okay, so where should we go from here? I think we should maybe grab a new sheet of paper, and I'm going to take a short little break. Alright, hell yeah. So what we're going to do is I really do think we need to, do the problem like this. Massive A, and then we're going to go over a pulley, and then we have, I don't know, maybe some bigger mass. Maybe this doesn't have to even be bigger, but we're going to show it like that, massive B. And then we do have a pulley, and then we have, and then we have a little ledge here. So booyah. And from this, let's just do the free body diagram of this, and then just on its own. Let's say this is just resting in place. That seems super simple, but you just never know. You never know. So I'm going to, again, draw this mass like it's in outer space. You know what I mean? Hey, it's just floating there in outer space. And then I'm going to go write F equals ma. And then from my problem, I'm going to be like, what do, and then again, I'm going to say we're just having and I'll draw it like this. This is the problem that I'm doing. We have a mass that's just resting on the ground. Okay, so from F equals ma, I'm looking at that ma mass, and what do I see? Is it accelerating this way? No. Is it accelerating up or down? No. There's no motion. So there you go. So this side is 0. But then, I break out my textbook and be like, is there known forces in the universe? Sure, there's still an Earth underneath this, so I'm still going to have a force down of gravity. So let's do that. Through the center of mass, I'm going to have Fg is mag. You know what I mean? That's the force of gravity. Now, this is the cool thing about free body diagrams. You just cut this thing out of outer space. And, I'm sorry, we're not doing this one. We're doing this one right here. So if I cut this thing out of outer space, I identified that force, but I know that it's not moving in that direction. So I have to have an equal and opposite. You know what I mean? This one's a little bit harder to see compared to the idea of having a tension. But we say this other force comes from the normal direction. You know what I mean? Hey, we're resting on the ground, and perpendicular to this resting, it is going to be a force this way. So we're going to say Fn. You know what I mean? Or usually it just gets an N, but again, I think it's good. It might be a good practice to label everything that is a force with an F character, and then just a subscript, like a subscript N. Okay, so now we can see from this, you know what I mean? Hey, the sum of the forces in the Y are equal to mass times acceleration in the Y, and we say that's equal to 0. So we get the sum of the forces in the Y is equal to 0, and let's sum them up. You know what I mean? We actually have down, Fg going down, and then plus Fn going up. So cool. So that's going to be equal to 0, and you can see that the force, this normal force, is equal to Fg. And so we have the force, the normal force is equal to mag, or just you can write it like this. N is equal to mag. Alright, cool. So that's going to be the normal force up. Okay, so yeah, that's just in this direction. But the cool thing about F equals ma is you can do it for all your Cartesianal directions. You know what I mean? You have you could be in the X, the Y, or just out and into the board. That's going to be the Z direction. So we can do this. We can say forces in the X direction, the sum of the forces in the X direction is equal to mass times the sum of the accelerations in the X. Or just, I don't know, the acceleration in the X. I forget how, I mean, obviously these are vectors. They both are. So I think you would also do the sum of the accelerations in the X. Just because, oh yeah, because sometimes if you're doing things in like circles, hell yeah, you might have an equation that the acceleration, you know, the normal acceleration of going around a circle with some sort of angular velocity is r omega squared. And so you know that, and that's this side of the equation, you know what I mean? But from our perspective, we're just going to say, hey, I just want an equation for acceleration, and all I'm going to figure out is the known forces. And so in the X direction, for this problem, we don't have any forces in the X direction, you know what I mean? So we're not going to see any motion in the X, And we don't even have one force. You know what I mean? There is not even one force. We don't have an Earth over here pulling it this way. So now we're just saying, hey, 0 forces is equal to mass times 0 acceleration in the x. Compared to the y direction, where we said the same thing, we don't have acceleration, we got eyeballs on it, but we observed there was actually one force. There was a gravity force down, but we're still observing that there's no acceleration, so there must be a force up to balance that if this thing, and I shouldn't have drawn this line because I just really wanted to iterate. You're cutting this out of the free body diagram, and you can put it into the deepest reaches of space and just like hold it there, and it's not going to be moving up and down, left and right, or rotating. Okay, hell yeah. So now I guess we're gonna do this one. You know what I mean? So if we do this, if we chop that into outer space, we know there's the Fg down. So I'm going to do force of gravity is equal to mass times acceleration times g. We know there's a normal force up. Force normal is equal to the same thing. That's going to be equal to mag, and then those are balanced. Okay, hell yeah. But now we have this tension in this direction. We have a force of tension. And see how maybe writing them like, hey, F and then the subscript. This might be useful. Maybe it's not. Maybe you're just really used to saying, hey, just do this as N and this is T, and let's get on with life. But I think this is fairly useful, because now if we know the tension in the cord, then we have this mass that we're analyzing, and let's go back to F equals ma. So F equals ma says, hey, so we are analyzing the mass at A. So we kind of dot that around, and we want to know the acceleration of this. You know what I mean? And obviously we're going to be in the x direction. That's the direction we're curious about. And so we've identified that there's a force in the x direction. So we know it, you know what I mean? So this is cool. So we have force of tension is equal to mass times acceleration, and we know the acceleration. And I guess I'll keep this subscript in the x direction. And we get something like this, then we can solve for acceleration. So we say acceleration in the x direction is equal to the force of tension divided by the mass of A. So now we have an equation for this change in velocity. Sorry, I'm just making noises with my seat. That is, you know, just chilling out. All right, so we have. Yeah, so that's the equation for acceleration in the x of here. But the only thing we don't know, we just don't know the tension force right here. So that's where we need maybe this other one. So we're going to chisel this thing out of outer space and do the same thing. So let's do that. So we have mass B. We have a gravity force. The force of gravity is mass BG. But hey, we don't have any force. We don't have any normal force underneath it. This is not resting on a surface. But we do have a tension force, so we have the force of tension. And guess what? The force of tension in this free body diagram is the same force of tension in here. So you could say this is the force of tension on A, and this is the force of tension on B. And you could say that the force of tension on A is equal to the force of tension on B. I don't know if you actually even want to get tricky like that, but just to show you that the tension in the cord is going to be the same. So that's exactly what we're showing. As long as this corner acts as a pulley, and there's a frictionless, smooth horizontal tube. So there you go, and it goes around a corner, which very much acts like a pulley. All right, hell yeah. So let's solve this free body diagram. So we say force is equal to mb, and then we dot around b, and then in this direction our acceleration's in the y. So we want to know the forces in the y, and we could have done this, sum of the forces, you know what I mean? Because hey, we got a few of them. We know that we have a force of tension up, so we have force of tension minus mbg down, and that's going to be equal to mb and then the acceleration in the y. But here, we do have continuity. This acceleration in the x, so we're going to say acceleration in the x is this same acceleration, just as this force of tension was the same in this free body diagram as it was in that. Our acceleration of this mass, because they're just moving in unison, is going to be the same. So that's the continuity there, and now we can just say that acceleration is now just a. So let's do that and just like get rid of this subscript. So I'm going to scribble it out, scribble it out, scribble it out. So now we can rearrange for A. We can say acceleration is equal to force of tension minus mBg divided by mB. Okay, hell yeah. And we're just slow rolling this stuff, you know what I mean? So now we have these as our acceleration, and I guess we can combine them together. So we can say force of tension divided by mass of A. And what I'm going to do is also get this. I'm going to divide each character by mB. So we're going to say this is the force of tension divided by mass of B minus, and then look at this. This is just minus G. Cool. So now when I say that these two are equal, I'm going to say force of tension divided by MA is equal to force of tension divided by MB minus G. Hell yeah. And now I can solve for the force of tension. So how am I going to do that? I'm going to move G over here. You know what I mean? So I guess we'll just do it in a million steps. We're going to go G plus F of T divided by MA is equal to force of tension divided by MB. Alright, so now I'm going to bring this over here. So I'm going to go G is equal to force of tension MB minus force of tension divided by MA. Alright, hell yeah. So now from here I'm going to factor out that force of tension. Like I said, a million steps. So we're going to factor out the force of tension, and we got 1 divided by MB minus 1 divided by mass of A. Hell yeah. And so now I can solve for force of tension. I can say the force of tension is equal to gravity. So we got gravity divided by 1 divided by MB minus 1 divided by MA. And hell yeah, so there we go. So now we know the force of tension. And if we go back to, like, what did we all do this for? Well, we wanted to isolate. And so now I'm going to actually scratch this, because this was just to show normal forces. But we really want to analyze the mass at A. We want to, for the problem it says, what is the velocity when the chain gets to this end? You know what I mean? So, what we're going to do is just do it one step at a time. If we have F equals ma, and this is going to be mass at A, and we know the forces on it, there's only one, and it's going to be the force of tension, you know what I mean? So we have force of tension is equal to, then we can actually figure out the acceleration. That's the force of tension divided by the mass at A, and now we have an equation, you know what I mean? So now if we throw in, and obviously this force of tension is just the gravity and the mass at A and the mass of B. So even right at the starting point, so let's do that. And it might not be pretty, but at least it's accurate. Acceleration is this force of tension, so that's going to be G divided by, and I'm going to put this MA first, you know what I mean, not to confuse you, but the F of T is G divided by this, 1 mass of B minus 1 mass of A. You can make the denominators the same, you know what I mean, and then once you get that, combine these into one, and then flip-flop it upstairs, downstairs. Let's do that right now. Might as well. So if we're just analyzing this thing, we're going to say, hey, how do we get the denominators the same? Let's do it in just a couple steps. So I want the denominators the same, so I got to multiply by MA, but that means I got to multiply by MA upstairs, because this is just 1. You know, I didn't do anything. And then MB, MB. So now this is just this thing in the parentheses is just 1, and so now my denominators are the same. So now this says this is MA minus MB, and that's it. So we I don't know if that really helps us out. But yeah, maybe it does. So we have MA minus MB, and then we have MA MB. And if that thing's downstairs, then we can flip-flop it and say that the force of tension is equal to G MA/MB divided by mass A minus mass B. You know, and again, I don't know if that was any better. But now when we go up to here, we can say, yeah, I really don't think, I can't see it. I can't see how that was any better at all. Oh, weird. It seems like I'd almost need to do it again. But if I did it again... Oh, this is tripping me out, and I really want to. So let's say I just did... No, you can't do it. You can't do it again. You can't stack this on that and this on that. That's not how that works. Only if you have... you can't have an addition or subtraction in your denominator. So anyway, well, let's just stick with this. This is cool. Because this actually simplifies to just G divided by MA divided by MB. I'm just foiling this in, and then this is going to be minus MA divided by MA, which is minus 1. So here's my acceleration. Okay, and this is going to be the acceleration right at the very initial position. It is just going to be gravity, mass of A divided by mass of B, minus 1. Okay, so hell yeah. So now we have our legit first check on reality that we can actually set up. And so what I'm going to do is set this up into Excel. And we're just going to what we're going to do is, because this driving force of mass B, this hanging chain from here to here, is always mass B. And what the hell did we say mass B was? Mass B was this length of the chain divided by the total length. And I should just, man, instead of L naught, I should say L total. But I feel like not, because this total length is going to change at any moment. Like this length might be here, and now the total length is actually a changing variable. The total length of the chain will vary, and then also the total mass of the chain will also vary. So you know what I mean. Also here, for the mass of the chain, it might be better to say this is m naught, because as the chain goes this way, the mass of the chain is going to go down. So just subscript wise, I just want to have a check on reality. But what we're going to do is we're going to do our first analysis, that we're going to say, hey, this is the acceleration, and we're going to say this part of the chain is going to be MA for the entirety. So even if it gets pulled down, and there's only this much chain hanging out, there is no chain right here. And so we're just going to say, when we let go of this chain, it's going to go all the way to the end, and we're going to try to find its velocity, velocity at the end. That's what we're interested in. But we're just going to make the assumption that the mass of that chain never changes, and so then we have this tension force that also, if we set up the initial problem where we have a massive chain that weighs, let's say it just weighs 10 pounds. Cool, and these distances are half. Then this part of the chain weighs 5 pounds. Cool. And I guess we should do it in newtons. So let's say this part of the chain weighs 100 newtons, and that's going to be like 25 pounds. The total chain weighs 200 newtons, and 200 divided by 4, the total chain weighs 50 pounds. Okay, so what we're saying is that even if this chain goes this direction, this driving force of this mass will always be 100 newtons. We're always going to have 100 newtons, and because of that, and then we're making the assumption that this part of the chain is also, like let's say 100 newtons for mass. But even if that was the case, if MA is equal to MB, that's fascinating, because this equation no longer works, and you get 1 minus 1 is equal to 0. Oh, so that's fascinating. I actually don't think this equation's right, so I'm going to take a little break, because if these masses are the same, it's only when MA gets small. Yes, if this gets small, then did I do this part right? Foiled it through. Yeah, but. Oh, damn it. Yeah, so I'm going to take a little break and then just, because this is crucial that we actually get this part right to set up an initial guess. Alright, hell yeah. So I love it when I turn off the camera and then just instantly kind of find my mistake. So, okay, so we're trying to simplify the problem. We're saying, hey, this is the driving force, and then we can figure out the tension in the chain. And even, I mean, even the tension in the chain, we're not even 100% accurate. You know what I mean? We're like even, well, no, are we? I mean, we did one scenario where the mass of B was just way bigger, and then we said, hey, we could figure out the tension that way. But since we did it with free body diagrams, I think we're good to go. The mistake that I was pointing out is that holy Toledo, I don't even know if I can even represent this. So we're just gonna grab a sheet of paper. It's total mass. That's kind of where I made the mistake. Is that we have the force is equal to the mass of A plus the mass of B. You know what I mean? And that's the acceleration. So we were analyzing like individually, you know, what the forces were on each individual thing. And I think that is okay to do. I think you can say, hey, if we chop this out of space, we're just going to have we're just going to have the force of gravity on this, which is the mass of B times G. Cool. And then we have the force tension up. And then over here, the mass of gravity times A is just the, you know, counteract with the normal force, but we're interested in this direction. And the only thing in this direction is the force of tension. And this is where, you know, maybe it's not very useful to write, you know, F and then a subscript T, because it's just, it's harder to see that this is the normal force, and it's harder to see that's the tension force. Okay, so the two individual free body diagrams work just fine, and we found what that tension force is, you know, by, and how the hell did we do that? Oh, well, we said the acceleration of A so the acceleration of A is equal to the tension. Yeah, so let's write this. So we have the only force on this is tension, and then that's going to equal to the mass at A times the acceleration of A. And then over here we have the tension. We have tension going down. The tension pulling up minus mass of B times G going down, and that's going to equal to the mass of B times the acceleration of B. And then we're saying the acceleration of A is equal to the acceleration of B. And that's how we found this force for tension. And I'm just wondering if I'm doing this fundamentally wrong, because at some point you have to, okay, yeah, this is fascinating. At some point, it's very beneficial to take a Pulley problem and make it in a linear direction. So this is what we're going to have. If we draw a line, you know what I mean, and on a surface, a flat surface, and sure, we can make mass of B bigger. But this is going to say, hey, we have the force of gravity is going to be mass of B, G, that direction. And we have the tension in this direction. We have the tension in this direction. And you can see how those cancel each other out. And then that's it. You know what I mean? So that's it. And then you just have normal forces in this direction. But in the direction of the path, which is always in the direction of the tension line, even though it goes over a pulley, this is a very good thing to do, because now we can use F equals ma on this, and this says F equals ma, and now the mass that we're analyzing is the mass of the entire system. So here's ma, and here's the mass at B. So we say the force is equal to the mass at A plus the mass at B. So yeah, and you could just do subscripts of A plus B, you know what I mean? Because this is what we're analyzing, the F equals ma equation. We want to get an equation for acceleration based on the net forces that we see. So if we have a net force, and we do have a driving force, and the only driving force is mbg. So we say, hey, we have a force. And even right here, you can put this thing into outer space. You can say, this is what it looks like, and we're attached. This was fascinating because this was, I was showing the tension in the cord, but the tension in the cord is irrelevant to the overall acceleration. Because if this is in outer space, the only force that we have is the force of gravity. And that's it. We have normal forces in this direction; they balance. You know what I mean? And then you have a net force in that direction, and then the whole system, the whole system's mass is mass A plus mass B. Cool. So now we have A, and we want to get an equation for acceleration. All right. So we have the force of gravity, and I guess we'll just do this in a million steps. Plus ma mb a, and then this force of gravity is going to be mbg is equal to ma plus mb is equal to a, and then so we can solve for a. So let's do that I guess right here. So we're going to say a is equal to this divided by that. So we have mbg divided by ma plus mb. And cool. So now we have an equation. we have an equation for the acceleration, and this equation for the acceleration. And it's just and it sets up that initial. You know what I mean? Hey, if this side of the chain never changes, and we have mass of B. And that's going to be the force on it. And then this side of the chain, at the mass of A doesn't change, you know what I mean, that'll be the force on it. So it was just so fascinating. It's good to run through all the free body diagrams, you know what I mean, but I just totally forget that Pulley problems, I do it this way. It's very useful if you're in a line to just take that thing and then put it on a straight line. But you still want to do the free body diagrams to see that, show that, hey, you got a tension force up and then a force of tension in that direction. And then once you get it on the line, those will cancel each other out. And those are internal to the rope itself. So if you are chopping away the entire thing, the only external force, those are internal forces. So the only external forces is going to be gravity on those links at B. All right, sweet. And now we can do our first check on reality. And this is still a guesstimate because, and I'll tell you why it's a guesstimate, is because this mass at A is going to change. You know what I mean? So as the chain falls, it's going to get way less. But we're going to do the first assumption that this mass stays the same all the time. Cool. So now with this equation, let's figure out what the acceleration is if we have 100 newtons here and 100 newtons there, or the mass of the chain in both these. What would be the mass of the chain in kilograms? So we have mass is equal to mg. That's going to be the force of gravity in newtons. So we have newtons is equal to kilograms times 10 meters per second squared. So if I have 100 newtons, that's going to be 10 kilograms. So cool. So I'm going to have 10 kilograms there and then 10 kilograms there. And sweet. Yeah, and 10 times 2.2, you know what I mean, that's like 22 pounds. That's what we were assuming. You know what I mean? Obviously, it's not an exact, you can't just take 100 newtons divided by 4 to get 25 pounds. It's going to be a little bit less. You got to take 100 divided by 4.44, and then that's a one to remember, but kind of 4.5 and almost 0.449. This is almost 100% accurate, so 22.47. Hell yeah. All right, so now we can find the acceleration given if these are all 10 kilograms. So we have 10 kilograms times 10 meters per second squared divided by 10 kilograms plus 10 kilograms. And now I see we have 10 divided by 20, that's half, and our acceleration is now just half. It's 5 meters per second squared. So cool. So even how it's drawn, we're pretty close, but obviously we want an equation where we can vary everything. Like we could make this hella short and this hella long, and we're going to have a bigger driving force. Like obviously we found out that this is our driving force, and it's driving it on the whole shebang. You know what I mean? Both masses are what's driving. And so let's say we just, and we're assuming that again this mass doesn't change even though the chain moves this way, and for sure this mass, once it gets to there, this mass goes in half, and then we can recalculate, you know what I mean? And so we'll do that. We'll do this a couple different ways, but the first, just to get just some sort of a clarity on this problem, is we've established, we threw some numbers at it, 10 kilograms, 10 kilograms, mass of the chain is total of 20 kilograms, and 20 times 2.2 is 44-pound chain. I don't know how many meters we want to do, but we could, you know what I mean? Maybe it's a fairly lightweight chain, you know what I mean, where this is 5 meters and this is 5 meters. I don't know, you know what I mean? So we could do that too, and then, okay, so I need to slow. This is the easiest part, but it might be the hardest part. You know what I mean? I don't know. But we found the acceleration. So we have 5 meters per second And again, this should be written as 5 meters per second per 1 second. It's a change in velocity of in 1 second, you know. That's what we're doing. So you can say at time is equal to 0. Hey, we just let go. This thing has a velocity of 0. But 1 second later, you know what I mean? So let's do that. 1 second later, this thing has a velocity. This end has a velocity, or this entire chain does, of 5 meters per second. And the entire chain, the acceleration and velocity of the entire chain is all the same. You know what I mean? Because it's just a connected unit. It's like a train. And so that's going to be the velocity after 1 second. So we have 5 meters per second. So now we need to find the average velocity. The average velocity is I guess we could do it this way. You know what I mean? So the average. So we went from 0 meters per second to 5 meters per second. So our average velocity is 2.5 meters per second, and we went for 1 second. So what's the distance that we traveled? Well, it looks like we traveled 2.5 meters. It looks like we traveled 2.5 meters. Okay, sweet. Cool. And so now we're not at the end of the chain, and so let's go for 1 more second. So if we go for 1 more second, we're going to go to 10 meters per second. And then what's our average velocity between these two? It's going to be 7.5 meters per second. So now in that second, we traveled an average velocity of 7.5 meters per second for 1 second. We went 7.5 meters farther. But now we just said we went 10 meters. You know what I mean? So maybe it would be more sensical to make this thing 10 meters. You know what I mean? So we want to make the problem as simple as possible, where it's like, hell yeah, we made that 10 meters. So it's a very lightweight chain. Could be like the ball chain fountain type of thing. You know what I mean? I didn't really want to talk about that because I will lose my brain and train of thought because, you know what I mean? I have my own way of debunking the mold effect of the chain fountain. I think it's ridiculous that, anyway, yeah, I don't even want to go down that route. Okay, so hell yeah. There's just a lot of fundamental principles from this problem that just exemplify the ball chain fountain, where you have very little weight at the top. See what I'm doing? You have very little weight at the top of the fountain, just pulling out very little bits of chain, where this is just down to just the very last little bits. And then you have a huge driving force of the ball chain if you throw it off like a deck. You know what I mean? So now you have this huge driving force causing an acceleration on just a very small amount of mass. You know what I mean? So But I don't know, you know what I mean? Because is that even the case for our problem? Because what we're saying is that, I mean, yeah, it's kind of bizarre, because what we're saying is that, hey, let's talk about that, because we're just saying, hey, this chain is in free fall, but it's actually attached to something, so it's actually slower than free fall, you know what I mean? Because it's taking some of its juice, and then the total mass is a little bit bigger. But once this thing gets down real small, hell yeah, the velocity will just be in free fall. So if I had this length of chain just in free fall, and it was able to, oh yeah, that is a fascinating one, because that would be the fastest this chain could actually go. So we're going to finish this one. So we have 10 meters per second. We had an acceleration of 5 meters per second, and we said that it's going to take 2 seconds. So a change in velocity of 2. Oh, and we said in 2 seconds it's going to be going 10 meters per second. So that's our answer to this one. So we already established that the velocity at the end right here, the velocity of this chain when it leaves this little fountain thing is going to be 10 meters per second. That is what we found, because we assumed that the acceleration was 5 meters per second because of that 10 kilograms. And I'm just going to make this 10 meters, because obviously if the chain is the same material and I have 10 kilograms there at 10 meters, I must have 10 kilograms here at 10 meters. But this problem is, hell yeah, you could vary these as much as you want. And then I was just wondering, well, what if you have like all the chain up here and just very little sticking out? Well, this problem still generates velocity because like that would be a more fascinating one, is just like, hey, let's have the chain like not be at the ground yet, and so you don't have all that driving force. But let's talk about that, because even from our equation, we're saying that the mass of B could be almost or 0. If the mass of B is 0, the acceleration is 0. So if both these are 0, our acceleration is 0. But let's say the mass at B is just 1/10 the mass at A. Cool. So you have 0.1 g divided by the mass at A, which is 1 plus 0.1. So now you just have 0.1 divided by 1.1. And 0.1 divided by 1.1, that's 0.09 g. You know what I mean? So now let's say g is 10 meters per second on average. So we basically just have 1 meter per second. So if that's the case, if this whole problem is and in that scenario, like all it is just that the ground is right there. If the ground is just piled up right here, well, now we just don't have a huge driving force, but we can still figure out our acceleration. We're going to say the acceleration, and I'm sorry, this is 1 meter per second squared. So now our acceleration is 1 meter per second squared. So for every second, so that's going to be a change in velocity of 1 meter per second for every 1 second. So now we're going to do the same problem. So in 1 second, we're going to be going from 0, and then we're going to go 1 meter per second. Okay. The average velocity is 0.5 meters per second, and we did that for 0.2 seconds. So we've gone 0.5 meters. Now for the next second, we go 2 meters per second. Our average velocity is 1.5 meters per second. For that second, we went 1.5 meters. Cool. So now the next second is 3, we go 2.5 meters. You know what I mean? Plus 2.5. And now let's keep doing that. 0.5 plus 1.5 plus 2.5 plus 3.5 plus 4.5. You know what I mean? So somewhere between, this was second 1, second 2, second 3, and in second 4, we're going 8 meters. And then in second 5, we're going 12.5 meters. So about 4.5 seconds. And how could we do that? Is 4.5 seconds the actual answer? Well, we say in 4.5 seconds, our acceleration changes by 1 meter per second. So that means we're going 4.5 meters per second. And our average... Oh, am I doing this right? in 1 second, I'm going 1 meter per second. 2 seconds, I'm going 2. 3 seconds, I'm going 3. And in 4 seconds, I'm going... Oh, yeah, no, we're doing this right. So in 4.5 seconds, our acceleration of 1 meter per second per every 1 second, that's going to be a speed of 4.5 meters per second. The average velocity, because we're starting at 0 meters per second, is going to be half that. It's going to be 2.25. But we did 2.25 meters per second for 4.5 seconds. So we go 2.25 times 4.5, and you get really close to 10 meters. So hell yeah. So in that scenario, our average speed is 4.5 meters per second. Cool. So now we have some check on reality. So if we actually get an equation for this, we can set it up where our height is 1/10 this length, and we will get a velocity of 4.5 meters. And yeah, if this is 10 meters, cool. If this is 10 meters and this height is 1 meter, we should see a velocity of well, and again, we probably have to stop making assumptions now from just general. There's no point in doing this anymore, because we're saying that the acceleration is constant, and we're making that assumption that this mass doesn't change. But in our problem, this mass does change. So now if this mass gets smaller, hell yeah, this 10 meters per second is going to go up. So let's grab a new sheet of paper. And let's keep on this one, because we're just kind of getting verbal confirmation that this is going to be the case. And yeah, this is a hella important drawing. So let's draw this one again. Because we have mass at B, mass at A. The only driving force is mBg, and it's going to be on the total mass. And so if we say F equals ma, that's going to be, the only force on it is going to be mBg. The total mass is ma plus mb, and what we want to know is the acceleration. So we can say the acceleration is equal to... and how did I have it written right here? Yeah. So it's just mb mBg divided by this, ma plus mb. All right, hell yeah. So now from this, this is where we said, hey, this is going to be 10 kilograms, and then this is going to be 10 kilograms at the start, and this is going to be 10 meters. And our acceleration is going to be 10 divided by 20 times g. G is just going to be 10, right? G is 10. And obviously it's in the downward direction. Okay, so now what we're going to say is at the halfway point, hey, this mass isn't 10 anymore. This mass is now 5. So our acceleration at the halfway point is going to be 10 times 10 divided by 5 plus 10. Which is 20 divided by 15. Cool. So now our acceleration, 20 divided by 15, is 1.3. Whoa, just a second. Did I mess up on the other one? Because I said this was 10 divided by 20 times 10, and that was going to be 5. Yeah, what am I messing up here? So here was 5 meters per second squared. And now this is going to be 10 times 10 divided by 15. Yeah, 10 times 10 is not 20. Sorry about that. Okay, so now our acceleration is faster at 6.6 meters per second squared. So now let's go one more. You know what I mean? Let's say when this chain reaches a quarter of the distance, what's the acceleration? You know what I mean? Well, the mass of the chain is going to be 5. So we have 10 times 10, and then this mass of A is going to be 5. No. I'm sorry, 2.5. Sorry. The total mass here is 10. When it gets to here, the total mass of A is 5. When it gets to here, the total mass of A is 2.5. So we have 2.5 plus the mass of B doesn't change. And now we have 100 divided by 12.5. Cool, and we get an acceleration of 8 meters per second squared. And I think, like, that should be good. Like, right now we should try to get an answer for the problem. Because check this out. You know, let's say you went to 3/4. Well, the acceleration is just going to be somewhere between there. It hardly changes. You know what I mean? So we could do that. That's going to be mass of B is 10 times gravity is 10 divided by 7.5 plus 10. So that's going to be 100 divided by 17.5, and we get 5.7. You know what I mean? So who cares though? You know what I mean? That's it's about the same. So now actually, because what I was gonna do, and I forget how to, like, sometimes it doesn't matter. We found the acceleration at the initial. That's gonna be 5 meters per second. Now I'm just gonna continue it like it's 5 meters per second to this point, and then switch it to 6.6, which is the acceleration at this point. But that's going to undershoot. That's definitely going to undershoot the velocity. And so let's say I took 6.6 plus 5 and then divided by 2. Well, hey, I get 5.8, and that's probably more representative of the total acceleration. And I just stored, I'm going to store this one at 5.7, store that as alpha B, 5 stored as alpha A, and then 6.6 we're going to store as alpha C, and so now we have those. So now we can actually do an approximation. We can say that the acceleration between this point, for the first quarter, is going to be A plus B divided by 2. I'm going to store that as alpha D. And then this point for the second quarter is going to be alpha B plus alpha C divided by 2, and I'm going to store that as alpha E. So now I could try to get the average between those 2 points. That's going to be alpha D plus alpha E divided by 2. So now I have 5.77 to be a more representative answer, and then that's really close to just that original alpha B. But now we could use this, you know what I mean? So I'm gonna use this as my approximation for the acceleration for that first half, and then what we're gonna store that as. So let's store that as alpha F. So that's gonna be my approximation for the first half. Let's find some approximations for the next little bit, you know what I mean? So for that third quarter, you know, maybe just halfway between 6.6 and 8. So we got plus 8 divided by 2. I'm going to store that as alpha I, and so now we have 7.33 for that last quarter. Cool. But yeah, that's where I don't know, because this last little bit, it could really pick up steam. So, you know, I mean, let's do 1/8. So what would be the acceleration at 10, and then we have mass at A gets real small. Let's say it's just 1.25 plus 10. So now we have 100 divided by 1.25 plus 10. And we get an acceleration of 8.8. But anyway, what is this approaching? I mean, this is literally approaching when the acceleration, when the mass at A gets to 0. I mean, again, it doesn't get infinite. I apologize. I thought the acceleration got infinite. My apologies. No, it just becomes a free fall problem, where hey, this problem is just in free fall. Because it's just so fascinating to turn a problem kind of into a simpler deal. Is you could just say, hey, let's say this whole length is this length. That's going to be the L naught of the whole chain. And look at this. This is point A, and what's the velocity at point A? It's 0. But now what we're going to say is, what's the velocity at point A when we go? And for our problem, we're going to say these are half. Well, if like right here, when A gets to there, what's the velocity at A? Well, it's just a free fall problem, and right now this is where it is good to use kinematic equations. We can say the acceleration is -10, and we can say that's going to be equal to dv dt. We can separate variables and say dv is -10 dt. We can integrate and say that velocity, and this is obviously the velocity in the y, is going to be equal to -10t plus a constant. At time 0, the velocity is 0, so we're good there. We can say that velocity is change in position, change in time. I just like to use the generic x, and we're going to say x is equal to 0, and this is positive x. So this is the x direction for this. And then we're going to separate variables. We're going to say dx is -10t dt and integrate. So now we have an equation for the position is going to be -10t squared divided by 2 plus, when t is equal to 0, the position is equal to 0. So there's our equation for a position. And now we're going to say when position is equal to, we're going to find the time. So now we rearrange this equation for time, and we say, so we go 2x is equal to -10t squared. We say 2x divided by -10 is equal to t squared. And then we say t is equal to the square root of 2x divided by -10. How does that work if this is a negative value? I never thought of that. Alright, hell yeah. So I hate negative signs, but obviously if our acceleration is in this direction, that's going to be 10 meters per second in the direction that we're saying. So gravity is going to be a positive number if we're saying this is positive x. Usually we say away from the center of the earth, like, hey, this is going to be positive x, but since we denoted it like that, our x direction is positive, our gravity is positive. Else, how this equation would work out is if we're saying -10, then this is our positive x, and then obviously this is negative x, or maybe not obviously, but then we would throw in a negative value of x, and then you wouldn't have that. So anyway, we're just going to turn these positive and then move on. And so, hell yeah. So this is the time. Now we can throw in our x is equal to, our initial length divided by 2. So we can say the time at A is going to be equal to 2 times the L naught divided by 2 divided by, and I'm just going to do G here, square root that. So the 2's cancel, and I have time at A is equal to the square root of L naught divided by G. And so now I can throw this into the velocity equation, and I can see that the velocity is just, and this is just gt. So sweet. So now I know my velocity is g times this, the square root of L naught, L naught divided by g. And how the hell do you get this out? You know what I mean? So let's do that. So this is the same thing as g to the square root of L naught divided by the square root of g. But actually, it's going to be way easier if you do it like this. G is the L naught to the 1/2 divided by g to the 1/2. And then even put a subscript on this. This is g. So now you could even go one step farther and say, hey, this is g to the 1 times, you bring this upstairs as g to the -1/2. L naught to the 1/2. So sometimes it's really useful to do it this way. And then you can see that this just becomes g to the 1/2, L naught to the 1/2. And then do it in reverse. So now this is the square root of g, square root of L naught. And then obviously you can combine the two. It's just the square root of g L naught. Okay, and so that would be the fastest. So this would be the fastest. So remember how we said in our problem setup, we would have if we're just assuming the mass doesn't change, we're going to have 10 meters per second. You know what I mean? So I think we have that. Now this is going to say that our velocity at A is going to be g times that length. And so our length is, now our length is 20. So we're going to have 10 times 20, and then we're going to have the square root of 200. So now our max velocity can be 14.14 meters per second. So hell yeah. So that's going to be a total check on reality. If it's just in free fall, And I think that's cool. That's the most highlighted part of this. If this thing's in free fall, and it's going to fall, and it's going to fall 10 meters. Well, we're saying this is 10 meters and 10. We're saying this whole length is 20 meters. So if it free falls for 10 meters, then our speed is going to be 14.5 meters per second. It would have been better. Yeah. Anyway, yeah. I think we're good there. And then we said that if the mass it is, and I can't. I'm just saying things over and over again. But if we say, hey, if this mass doesn't change, and then we still have that same driving force of this, then that speed is going to be 10 meters per second. So now we know, we have a check on reality, that our problem has to be somewhere between 10 and 14. Hell yeah! So I'm going to take a break. All right, hell yeah. All right, so we went over the problem where we know if we get the right answer, it's got to be between 10 and 14. And you know, I might have made a mistake. You always have to leave room for that if you think you know, that wasn't an appropriate analysis. But now we are going to, and it was kind of cool because we figured out what the acceleration was when the mass gets reduced. You know what I mean? From that equation. And so I guess let's just write this one more time. So we have the mass at A, we have a length of chain, and then we have the mass at B, and mass at A. And then we have a driving force, which is the mass at B times gravity. That part's not going to change, but the mass at A will change. Okay, and so from that we got the equation for acceleration is mass at B times g divided by mass at A plus mass at B. Now, you know what I mean? Because even right here, what I want to do is now throw this into Excel in the easiest way possible. So I just want to know the velocity at this end point, and so what I'm going to do in Excel is I'm going to say, hey, at time 0, I'm going to say this is position x. So x is equal to 0. So x is equal to 0. My velocity is equal to 0, but my acceleration is going to be this equation. You know what I mean? And so so we still need, in Excel, we still need the mass total of the chain. So we're going to say the mass total is 20 kilograms. We need gravity. We're just going to say that's 10 meters per second squared. Now we could, I like using 10. We could always go back and use more accurate values for gravity, like 9.8. But man, it just makes the problem so much simpler to intuit if you use 10. Okay, so now, and then we need to know the mass at A. And then so that's going to be a fraction. So we need to know our height. And I guess we're just going to set it up. I mean, we can change this height to anything, but we're going to say this height is 10 meters. And now we need to know, and I'm going to say this is the initial mass of the chain, right? And then we need to know the initial length of the chain, and I'm going to say that's 20 meters. So now, so even for our air acceleration, we need to know what this length is. So I'm going to say that the length of A is associated or proportional to the mass at A, and the length of B is proportional to the mass at B. I'm just saying whatever chain's remaining, I'm going to call that length of A. So I'm going to say, so now I need an equation for that. So I can say, because when x, well, let's just say when x equals length of, oh man, how am I going to say this? Oh, okay. I think the first equation we need is length. The initial, length at A initial. Sometimes it's just, I like using this initial subscript, you know what I mean, like naught. LA naught is going to be the initial length at A. And so that's going to be this length. That's going to be the initial length of the chain, which we know is going to, the length of the total length of the chain is actually going to shorten until it goes, and is basically going to be h. So the actual length of the chain, and we're going to say as a function of x, is going to be is going to be greater than or equal to h, but less than or equal to h plus LA naught. So I don't know, you know what I mean? Like, that was cool to write, but you don't have to, I don't think you have to know how to write something like that, but you can just intuit that that this length is going to be, what are we saying? Oh yeah, this length is going to be the initial length of the chain minus h. Cool. So now we just want to know what this is. So let's say x. We're going to go 2 meters. So x is equal to 2 meters. So if that's the case, I'm just going to write it in right here. If x is equal to 2 meters, what is length at A? Length at A is going to be well, wouldn't it just be this? Wouldn't it be this minus 2 meters? You know what I mean? Because we still have that. That's why doing this not is really nice, because the initial mass won't change. The initial mass, the initial length won't change. You know what I mean? So this initial length at A is always going to be 20 meters minus 10, so that's 10 meters. But then when we go in 2 meters in x, you know what I mean? Hell yeah! Now this is going to be 8 meters. So it's as simple as saying LA as a function of x is equal to L naught minus h minus x. You know what I mean? So hell yeah! So now we have LA as a function of x. So at any, and you don't even have to write this x, but it's just kind of useful. I mean, obviously this is velocity as a function of x and a function of time. At this time, I mean, you're actually setting it up to be, this is also a velocity of a as a function of t, because you have, your t value. But okay, so when x, so yeah, we're just going to write it in. So this is L naught minus h minus x. So when x is 0, hell yeah, this is just going to be L naught minus h, and then we're good to go there. Now for our, holy hell. So now we need, oh, I'm sorry to erase that, but what we're trying to find is the mass at A. The mass at B won't change, you know what I mean? Sweet. The mass at B is always well, yeah, the mass at B is going to be proportion. So if we know the total mass, so the total mass is proportional. Do you do that as that proportional sign? The total mass is proportional to the initial total length. I should say the initial total mass is proportional to the initial total length. Okay, hell yeah. So that means that the mass at B is proportional to h divided by you know what I mean, the time, so it's going to be that proportion. Whatever this is divided by the total length times the mass of the initial. Yeah, so there you go. So that is, and that's going to be the mass at B always. You know what I mean? So it's always going to be like this. So we can totally just write a hard equation that the mass of B is always just going to be h divided by L naught times m naught. So we can have we can in Excel have a line for this that is just going to be that, and this won't change. As we bring this down, that value won't change, because all these things are just given and initial conditions, and h doesn't change. All right, but this mass of A does change, because we can say the mass at A is proportional to the length of, how do you say this? Okay, I'm actually going to pause the video because it's intuitive. It seems like it makes sense intuitively, but I just don't know how to write it as an equation. All right, I turned the camera off for just literally 2 seconds because I don't know what this one is, but I do know what the initial mass at A is. You know, we can write that. The initial mass at A is proportional to the length at A divided by L naught times the initial mass. So at the initial condition, this is the mass at A. And that was cool because now it makes sense. Now I just know that the mass of A as a function of x is proportional to LA as a function of x divided by the length naught, mass of naught, the initial mass. Or is it the initial? Whoa, just a second. Because I said the length of A, the length of A as a function of x is going to be the initial length minus h. So this value is going to be the initial length minus h minus x. So this is going to be the remainder length. That's what we're saying. So no. This is, if we say this is the remainder length, yeah, okay, so let's say the whole chain weighs 20 kilograms and it's 20 meters. Oh, that's totally our problem statement too. And then that makes it really easy because now for every 1 meter of chain we have 1 kilogram. And so we're going to say when x is 2 meters, we need mass of A to be 8. So let's just try it out. So the length at A is going to be 8. 8 divided by 20 times 20. You know what I mean? So that gives us a mass. This is the ratio of lengths, but then times 20 kilograms. So this gives us a mass of 8 kilograms. So that actually worked out. So now I think I have an equation for mass. Mass A as x is going to be LA as x. And I don't need to rewrite this equation a million times. I can just write it like that. So right in here I can say the mass of A is LA of x, which I have in this cell, times, or divided by the initial length, times the initial mass. Whoa, you know what I mean? So now when I just have 1 meter, when x is 9, so let's try that one. When x is 9 meters, the mass at A should just be 1 kilogram. And so if I throw in 9 meters here, I'm going to have 20. So we have an initial length of 20 minus 10 minus 9. And then, so this is going to be 1. And then I'm going to do 1, and then now it makes sense. 1 divided by 20 times 20. And, and we just set it up where our kilograms and our meters are the same. But we're trying to set this up so you can change these values to anything you want. The reason that I'm just setting it up in values that make sense to me is just they're just really crisp, clean numbers. You know, so heck yeah. So now we have it. This is the equation for mass at A. Okay, and what we're getting to is like basically we just need to find this acceleration. Because once we know that but the acceleration is a function of these things, the mass at A and the mass at B. Because let's write it. So there's our function for acceleration, and I guess I'll just write it in. It's mass of B times g divided by mass of A plus mass of B. Cool. So at this point, our acceleration, obviously for our problem, is going to be 10 kilograms times 10 divided by 10 plus 10. So that's going to be 10 divided by 20. That's a half. So we have half g. This is going to be 5. But as we go, and then so in Excel, because I'll do this every time, because I was just thinking, I'll just do it maybe like once and just have a couple videos on using Excel. But this is the heart and soul of my teaching strategy when we're just learning F equals ma. Hey, we sum the forces. We know what mass we're dealing with. It's actually going to be the combination of both those. And then we want to get an equation for acceleration. Well, that's just going to be the sum of the forces divided by the total mass. So that's basically what we did, and that's the equation that we have. But this equation is only going to be for that instance in time. Once this starts to move, whoa, our equilibrium shifted. You know what I mean? So this mass changed. This driving force didn't change. So that's why this problem is fairly simple, even for being kind of a challenging one. All right, so then the next thing in Excel is to, if you do know the acceleration, what the hell is acceleration? Acceleration is change in velocity, change in time. Write it like this, dv dt. And we are saying, like, hopefully this is the true acceleration at this point that will be the same acceleration even at time, you know, is equal to 100th of a second later. You know what I mean? And that's why you want to make this time value small enough where this acceleration doesn't change. Because I was just thinking, this is where I just say, hey, this is our acceleration for the next 0.01 seconds. But that's not true, but this is just my simplistic way to do it. But when we get to velocity, no, I do say it's the average between the two. But right here, we don't have a. I think it would be a circular reasoning. Like we don't know what this next position is, because we have to at least pick some sort of acceleration. You know what I mean? So we pick some sort of acceleration, and that's from this equation. And then we rearrange this. This is an equation of three things. You can rearrange this equation any way you want. You know, you got three equations here. So we're going to solve it for dv. dv is just the dt upstairs, acceleration dt. And now we know what that is. That's going to be our acceleration, that 5, times our change in velocity of 100th of a second. So now we're going to have 5 times 0.01. So now we have 5 hundredths in meters per second. That's going to be our change in velocity. So we have that as an accel right there. And so then we say, what's our velocity? Right here is going to be, this cell is going to be this plus our dv. You know what I mean? So that's going to be that. Okay, so now we write what's velocity. Velocity is change in position, change in time, or dx dt. And again, we have three things here, but this is the only thing where, okay, now we do know what our velocity is at two different points. We know it started at 0, and now it's plus this little change in velocity. So we do want to take the average velocity. We don't have to have a circular reasoning. We know what those 2 points are. So from starting at 0, going up to this velocity, hell yeah, the average velocity is just halfway between. And so we set a new column, and I'll get down here. Like, obviously these columns are just in a row this way, but our new our velocity average is 0 plus that 0 plus dv. You know what I mean? Those two terms, and then divided by 2. So for the first term, it's just dv divided by 2, but as we go, our average velocity will be this plus this divided by 2. So that's this term right here. And then we can rearrange this for dx, you know what I mean? Because we have an equation with three things. We can have three equations. We can solve for velocity average, we can solve for dx, and we can solve for dt. To solve for dx, our change in position, that's all that says, is just bring the dt upstairs. So we got our velocity average dt, and now we know that our velocity average is this cell, and we'll get a new cell for dx, and we're going to say, hey, this cell is this, times our dt, which is 0.01 seconds. And this is where the kinematic equations really shine. It's like, whoa, we did two things, two different things got multiplied. Our change in velocity got multiplied by this change in time of 0.01, and our change in position got multiplied by 0.01. So if we go over the kinematic equations, or if you do remember them, you can say acceleration is 1/2 gt squared plus initial velocity t plus initial position, you know what I mean? And then you can say the velocity is going to be gt plus the initial velocity, you know, and then you can say acceleration, well, that's just g, you know what I mean? So for free-falling objects, g is your acceleration, that's why I used it. But obviously this could just be a. But yeah, so that's basically what we're doing, but just in an Excel way. So now we have the change in x, and so now here, this value will be 0, it'll be that top value plus our dx, you know what I mean, plus dx, and then we can just start the process again. And what we're going to do is run this time frame in the same increments, because all our change in times will be 100th of a second, let's say, and then we'll go to where x, because what we're really curious about is where this value becomes 10 meters, and then we'll have a velocity associated with, let's just guess, I'm just going to guess 13 meters per second, and sweet. And then our acceleration, hopefully it's in free fall. Hopefully at that point, you know what I mean, our acceleration will max out at 10 meters per second just as a free falling object. Alright, hell yeah. So I'm going to go to Excel, and then I'm just going to catch on the flip side. Hell yeah. So we're in Excel, and yeah, I don't mind showing this, you know what I mean? So I just come down here and then throw a time value. I do everything in lowercase. So we have time, we're going to go 0, we're going to go 0.01. And I don't even know what the hell I did. So we're going to go 0, and then we're going to go down 0.01. And I don't know. We're just going to take this to, you know, a bunch of seconds. And then maybe control home, get back to the top. So my next is just the x. And this is going to be in meters. You know, I mean, you can always put the meters up here, you know, I mean, seconds up here. And this is going to be 0. And then the next column is going to be velocity. So it's meters per second. And holy Toledo, I'm going to try to center everything. There we go. Yeah, it's going to be way better. I didn't do that last time, and I just got kind of confused. So this is meters per second squared. Whoa. Or just meters per second. Cool, and this is our acceleration term. So now the next term is LA of x. You know what I mean? So we have that term, and this is in meters. And then we have mass A of x. And then we just have mass B, and we know that that doesn't change. Sweet. And that's going to be in kilograms, and so we have kilograms. Okay, what else? So now we're going to have dV. So we're going to have dV. I guess, yeah, I'll just do that, dV. And then we're going to have average velocity. So I'm just going to do V average. And we got meters per second. And we got meters per second. Cool. And then, so after average velocity, we have dx. Cool. So we have dx, and that's going to be in meters. What I always like to do is just kind of write these, I'm going to say acceleration is dv dx. You know what I mean? So, dv dt, and then I'm going to say right over here that dv is equal to acceleration times dt, just so you can see it. Then I'm going to go over here and say velocity is dx divided by dt, and then write dx is equal to velocity, and I guess this is average, you know, we got to keep it real, times dt. Okay, so yeah, this is going to be velocity average. It doesn't need to be, as long as your time frame is just super absolutely tiny, you know what I mean? But nah, I think it definitely should be. I haven't assessed it. I just don't think I can do the same thing for acceleration because it would be a circular argument. I don't know. So holy Toledo, what did we do? So we're just going to get this down 1. Booyah. Alright, so now our initial velocity is 0. And so we're going to have to throw in some of these values. So our m naught is going to be 20 kilograms. Cool. And now we have our g is going to be 10, and we got meters per second per second. Cool. And now our height is going to be 10 meters. Heck yeah. And holy Toledo, we need to insert some cells. So just going to highlight this and just insert. We might need to insert quite a bit, so we'll do. Didn't want to do that. So yeah, we'll just insert that many more. Thanks for bearing with me. So now we have L, capital L naught. That's going to be 20 meters. So all these things we can vary, you know, and then still run it in Excel. Because what we're trying to do is get, you know, use the calculus to get a, and I think this one requires a natural log. Like, I haven't seen this problem, but I accidentally glanced I just wanted to make sure it was the right problem online, and I kind of just glanced at the solution, you know what I mean? So it was a function of natural log, but other than that, you know what I mean, that should be obvious to me, even though it's like, well, I guess it's not, but yeah, okay. Cool, so that's going to be that, and I think we're good to go. So now we're going to say this LA, especially LA naught, and we could write it out. We could say LA naught, LA naught. You know, that's just going to be L naught. We can just write this out as an equation. Is going to be equal to LA naught is equal to L naught, that initial length, minus H. Cool. So you know, just so we have something to look at. So I'm actually gonna get this over there. Heck yeah. Okay, so but now we need to know that this LAX is going to be this initial length of 20. Now you have to hit function 4, you know, F4. So, and it's just the function key and then the key above the number 4. I don't think I can reiterate that enough because sometimes it's really difficult to find where the function keys are. But that puts double dollar signs on this, and that won't change the value when we drag it down. So that's L naught, and we're going to say minus H. Same thing, F4. So function, and then the key just above the number 4 on your keypad. That's going to be the function 4 key. It's going to put double dollar signs. Okay, but now we're going to say minus X. You know what I mean? So heck yeah. And this doesn't get dollar signs because now when we drag it down, like we drag it down this, look at where this function is. These did not change, but now this went to the next little value. So I'm just going to undo that. So now our MA of X, same thing. So we can do that same thing just so we have a check on reality. What's MA naught? Well, that is going to equal a ratio between MA or LA naught. So it's going to be equal to, let's get this. It's going to be LA naught. I didn't need to do that, but whoa. Let's get this up here so we can see it just a little bit better. So and get it down one. Okay, heck yeah, feeling good. So we have LA naught divided by L naught, so the total length, and then we're going to multiply it by the mass M naught. You know what I mean? So these are things that we already just did on our sheet of paper, but in Excel it's just a second opportunity to really hone in exactly what's happening. So that's going to be the initial mass. So now we can definitely see that this mass is going to be LA of X. So I can even do parentheses here, divided by L naught. I got to do function 4, and then end parentheses, and then multiplied by M, the initial mass. So and we're going to go up there, and then function F4, enter. Heck yeah. So now we need the mass at B. And I guess we need an equation for that. Mass of B is equal to LB, which is the height. So cool. So that's just going to be a ratio between the height, L naught, times M naught. And that won't change. So booyah. So we're just going to go parentheses, height, function F4, divided by L naught, function F4, parentheses multiplied by M naught, and all of those require function F4, dollar signs on them all. It's just a constant, but when we pull that down, like obviously they'll all be the same number. So when we pull this down, this one is still registering those values. So hell yeah. Okay, so now we need to get this equation for acceleration. Let's write that in. Our equation for acceleration was going to be MB. So we have that. So capital MB. Okay, and then times G, and then we have divided by parentheses MA as a function of X, I guess. Yep, MAX, and then plus MB. And MB is just not a function. It is a function of X, but it's not. It doesn't have X in it. You know, it doesn't matter where X is. MB is still the same. Cool. All right, so that's going to be our equation for acceleration. So let's do it. So we have MB So that's going to be this one times max, and no dollar signs on these because we're going to drag them down, okay? And then divided by parentheses max again plus mb again. Cool, heck yeah. And there you go. So that's our 5. So we have our checks on reality, you know what I mean? And now we can say, hey, what's change in velocity? Let's go up here. dv is equal to acceleration. Cool. So that's going to be equal to this acceleration times our change in time. Now, you could just write 0.01 and then drag it down. You know what I mean? Do we want to do that? Or sometimes I do this. This minus this. You know what I mean? Because that's going to give us the same value. But for the sake of time, because you know, then I could change these up later. So yeah, let's do that. So we might want to change these up later, make it just a little bit longer. So we're going to go this minus that, and booyah, that's going to be our change. So now we need our velocity average. That's going to be velocity average. And holy, what am I doing here? Oh, no. We didn't write an equation for velocity average. So, so velocity average is going to just equal velocity final plus velocity initial, and there's no order on those because it's addition. You know what I mean? It's not subtraction. We don't care about the absolute value. Whoa. Divided by 2. Sweet. So that's that function. So we're just going to say this is going to be oh, and so we already have our dv, so we can go right here and we can say, hey, this is going to be equal to plus our change in velocity. So really straightforward. There you go. So now we can find our average velocity. Parentheses, it's going to be this plus our initial divided by 2. I think it's just a good habit to get into final plus initial. It doesn't really matter, but it's just the average between them. Just because if you do the difference, it's final minus initial. But yeah, that's who cares. And so that's going to be our average velocity. That means we go up here to our equation for dx is average velocity times dt. So that's going to be this cell times parentheses the difference between time. Whoa, this is subtraction. There we go. Cool, so now we have dx, and check it out. So our dx hardly moved. It moved a quarter of a centimeter, you know what I mean? So, I mean, a quarter of a millimeter. You know what I mean? So, because this is in meters, you know, you go 1, 2, 3, that's 0.25 millimeters. Cool. So, this is going to be our initial x plus our dx. And just such a cool, clean way to do problems. You're like, no way, I could have just, like, all this required was what our acceleration was initially, and then set it up and get a new value of x. And then it's really good for integration because we can be like, oh, well, yeah, now my parameters changed if my x changed a little bit, and that's exactly what we did. So we can pull down this equation for acceleration. Oh, hell no. So where are we at? Whoa. So the equation for acceleration, it's fine. I just have to pull them down all at the same time. You know what I mean? So there you go. So let's say it was this, because we already knew at this new x value what our max. So some things like these could have been in front. Like, hey, we know x. That means we know lax, max. Cool. Those should have been out here, and then we can pull down our acceleration. We just did it in kind of the wrong order, and then we can go here and see that our acceleration. Well, heck yeah, it's going to be mb times, oh, and I think I messed up, because isn't this times gravity? I'm so glad I caught that error, because yeah, acceleration, you probably caught it a long time ago. Acceleration is mass of b times gravity. Whew. And then we definitely need dollar signs on this. Enter. And then so even though gravity and my mass of b were the same, but yeah, that was brutal. So here, this term is going to be gravity, and we're going to go dollar signs. All right, heck yeah. So now when I pull that down, it should be the same term. And just to double check. So this acceleration I have is mass of b. So that's what we have here, this blue term, mass of b times g, and we got dollar signs on that, divided by mass of a plus mass of b. Hell yeah. Okay, so nice. So now we can just pull this down, and what we're looking for is when our position is going to be at 10 meters. You know what I mean? So we'll just pull it down to here. Hey, look at our position. Oh, you know what I mean? This thing is going cranking slow, so it's just really slow.
maybe our time value is not big enough. But hell yeah, 4.7 seconds? No, heck yeah. So we're good to go. So now we're going to go up and actually just go to the beginning. So we're just looking at this column. When our x, so now we're going to go down. When our x is at 10 meters, that's when we're going to call it. And then we're going to figure out what our velocity was. So heck yeah. So right here it's at 10 meters. So I always do like one extra because some of my equations require the bottom two. So we're just going to erase all this and then highlight this. Because this is at 10 meters and we have a velocity of 11.6 to 11.7. And you can do a linear approximation, or you can just see that this is way hella closer. So basically, I'm just going to say is equal to that cell. And this is going to be our acceleration. This is going to be our velocity. So we have a velocity of 11.77 meters per second, and it sounds like an answer in the back of a textbook. I'm just joking, but no, there you go. And that was between 10 and free fall. So yeah, it was between 10 meters per second and free fall. And so we're pretty satisfied that we know what's going on. And is there anything else? What was our acceleration right at the end? That's what we wanted to find out. And hell yeah, our acceleration right at the end is 10. That's free fall, and that's what we should expect. And so yeah, that's way cool. And what we could do is do velocity as a function. So what I like to do is just insert another column, and then just copy this. So we got copied. We're going to go Control up, and then I'm just going to paste it in. So now I'm just going to do a graph of time and velocity. Because that's what we kind of want. We want velocity as a function of time. There we go. So I'm gonna go. What do we want? We want to insert a chart, and you just need to scatter. I guess anything. Scatter plot. So the scatter plot. And then you click on here, right-click it, and then add trend line. And then we're going to go logarithmic. Whoa. Oh, it can't calculate it because we got negative values. So let's not start at 0. Or we have 0 values or something. Let's start right here. I'm curious if we can actually, I've never done that before, of actually plotting. So I'm going to click on it with my left mouse and then right-click it, add trend line, come over here. We're going to go logarithmic. No, it hated that. Exponential. No, linear. So yeah, for whatever reason, it won't do a natural log. Yeah, I don't know why. You know what I mean? Yeah, it just doesn't like it. But anyway, so I'm going to end the video here. So we had an equation for velocity. Yeah, so here's our equation for velocity. So it starts to free fall, so it starts to go exponential, but it's less exponential. It's like we have a constant acceleration causing a constant change in velocity. Yeah, if we have a constant acceleration, this velocity is going to be constant. Oh, and if it was in free fall, we'd have constant change in velocity. We would have a straight line here. But because our mass gets way smaller at the end, we have an uptick where that velocity definitely increases. We have a huge driving force over. But again, this is this tangent line right here is gravity. This is the line of gravity. If you have, so let's. But I think we're done. So let's go back to pen and paper. Thanks for joining me on this one.
All right, hell yeah. So now we can integrate. You know what I mean? It's just like, holy Toledo. It's like, it makes it so simple when you do it in Excel. So now what? Well, we want to take that equation for acceleration. And so, where was that? The equation for acceleration was right here. So we're going to start with that. We'll hopefully just do it in one sheet of paper. But we have mb of g, but now we have ma, and this is a function of x, plus mb. So now we have, and we know what ma is a function of x. We just did it. We said that ma of x is equal to la of x divided by L naught divided by M naught. Cool. And then we said LA of x is equal to, that's going to be this is what it is. It's L naught minus H minus X. So hell yeah. So holy Toledo. So so then that means that MA of X is equal to L naught minus H minus X divided by L naught. So we can simplify this. This is just 1 minus H divided by L naught minus X divided by L naught. And this is just a constant, you know what I mean? So just know that. This is the only term that has X in it. So now let's throw that into our acceleration equation. And holy Toledo, we need to know that acceleration is dv dt. What we did in Excel is exactly what we're going to do here with integration. We just made a tiny change in t, and then we said that if we know the acceleration, we know that the area under the curve of the acceleration, let's talk about that. You know what I mean? So if we have time and we have an acceleration, it is meters per second squared, and then we have time in seconds. You know what I mean? If we have something that's constant, area under the curve, and what the hell is the area under the curve? Well, it's this units of meters per second squared, you know, and that's going to be this height, and then this length is going to be meters of seconds. So when we get the area, that's going to be the multiplication of those. So the units become meters per second squared times seconds, and then 1 second cancels, and now we're left with the area of this is in units of meters per second. It's in units of velocity. And so that's the whole reason of separating variables. Acceleration is dv dt. Separating variables and then integrating with integrating and getting an equation for velocity. Now here's the catch. If any of your acceleration terms, especially when it comes to like viscosity or you know, it's usually, whoa. Well, I don't know. We'll get to that in a second. But I do know, yeah, we'll see how this one turns out. Man, this is the sucky thing. Actually, the viscosity one I think is easier because you have your acceleration or your force. If you say F is equal to ma, well, your force, you have a force of, you have mg, you know what I mean, downward, but then you have a resisting force upward of like a steel ball falling into the ocean. You have a force of drag upward, and that force of drag is some constant times velocity. So then you get this. You have constant times velocity is m, and then you just do this. This is dv dt. But then when you separate variables on this one, yeah, we'll do this one just for a second. Well, you don't have, you know, you have like a, let's see. Oh yeah, it's just that you need to use the chain rule, and it's just like, damn it, I wish I like, yeah, you can't just say, hey, this is dt and this is dv, and then get an integration, say this is just v as a function of this t, because you just have v in two different places. Like obviously, if this is your dv, here is a v, and you need to collect variables. So what we do with this dv dt is do the chain rule. So we say acceleration is dv dt, and we say that's equal to dv dx, and then dx dt, and then we see that this is the definition of velocity. So we say dv dx of velocity, and now we don't integrate with respect to time. We integrate the other side with respect to position. You know what I mean? So then you would get mg dx over here, and then you would subtract over here, you would get m yeah, I forget, but m plus kv, and then well, yeah, let's not do that problem. You know what I mean? You just well, let's see if we can. Well, we might come back to that one, because that is a good one to like rehearse. You know what I mean? Just so you kind of know how to do these. Okay, so we're going to have acceleration is dv dt, and we'll just throw it in one time. So we have mass of B, G, mass of A of X is the monster. You know, I mean, this is going to be 1 minus H L naught. But even right here, like, hey, you could just loop this into a constant. You could just call this constant A, and you could say A minus X L naught. You know what I mean? So we might do that in a second. Okay, so we have, so minus X divided by L naught. All of that is mass of A. And then we're going to say plus mass of B. Okay, sweet. So now, and then we just know that the mass of B is equal to the height divided by L naught times the initial mass. Cool. So yeah, you know what I mean. We could put that in there too. And let's try that out to see if we can kind of simplify. You know what I mean? So we got 1 minus H L naught minus X L naught plus H L naught M naught. You know what I mean? So we have a lot of things with L naught in them, so we could go, we could say 1 plus 1 divided by L naught times negative H minus X plus H. But this is H M naught. Yeah, I don't think it's worthwhile separating that out there. I mean, in the end of the problem, we will have to say that MB is this, you know, but this is just a constant anyway. We already know that's a constant. All right. So yeah, so this doesn't simplify any better. I don't think so. Okay, so we're gonna scratch that and then just keep motoring. Okay, so let's do our thing. So now we have dv dt, and let's get this on one side. So we're going to say mbg divided by 1 minus h l naught minus x l naught plus mb. Because right here, this is the only thing that has x in it. All this stuff you could say is just a constant. You know what I mean? So this is going to equal dv dt, but we need to use the chain rule. Say it's equal to dv dx, dx dt. See, all we did is we took dv dt and then multiplied it by dx dx. You know what I mean? Just the position, the change in position divided by the change in position. And then we just kind of just rearranged. So then we say, hey, dv dx is dx dt, because we know what dx dt is. That's the definition of velocity: change in position, change in time. So this is going to be equal to dv dx times velocity. So that's what we get. So we say dv dx times velocity, and so now we can integrate this side with respect to velocity, and then we can take this dx upstairs and then integrate this side. Cool. So let's do that. So we're gonna say this mbg divided by 1 minus hl naught minus xl naught plus mb times dx. All right, hell yeah. So we're back, and I had to take a longer break, and so we were using the chain rule to get this over here as a function of dx. And so yeah, where were we at? So yeah, so we got this is dv dt. This is equal to dvx dx dt. This is equal to dv dx v. And so all we did is we just got the dx term over here. So this is going to be equal to v dv. So all I did was just switch places with these. And now I have a function. So now I can integrate both sides. And we can integrate with respect to dx, and you know, at the end of the day, this is something. What we have here, we do have a negative. You know what I mean? So we have you know what I mean, maybe a constant. We're just going to say d divided by a constant e minus a constant. I'm not going to use f, but g of g of x. So there you go. So this is kind of what we have, and and so maybe the first thing to do is like, well, I think let's do this over here. Obviously, you could simplify this. So this is what we're going to do: mbg divided by 1 minus h divided by L naught minus for this. For this term, if we had x and then we multiplied by an L naught upstairs, hell yeah, we would just get x as a factor of 1. But we can't just do it to that term. We would have to do it to every term. So now we could just multiply by L naught. So then this term, well, let's do it in a couple. So this becomes L naught minus h minus x plus mbl naught. So there you go. So now the constant form is going to be L naught minus h plus mbl naught. Cool. So minus x. So there you go. So now here we have some sort of constant minus x. So I'm going to say, again, this is like a constant upstairs plus b minus x. So that's basically in the form that we have it. We're going to say a is mbg, and then b is going to be that term right there. I don't want to write it again. Okay, hell yeah. Okay, before we take this to Excel or actually integrate it, we're gonna kind of take one more look at it. So we're gonna get it in this form where you have the integration of a b minus x is equal to the integration of v dv. Now this is just v to the 1, so we integrate, we're going to get v squared divided by 2. And how do we know? Even that is just like, well, if this is v to the 1 and we integrate, we get v to the 1 plus 1 plus 1 divided by 1 plus 1, which is just 1/2 v squared. So hell yeah, plus a constant. And so that's this side of the equation. This side we'll have to look up in a book. If this side was just 1 divided by x, the integral of this is just natural log of x. So this is what we would have. But now we have so we have a constant plus x. So that's gonna be a little bit harder. I don't know how to like make this not have, I don't think you can. I don't think there's a way, but I'm sure it's going to be like a negative natural log of x, or like, something minus the natural log of x, for this term right there. But we're going to look that up in the book. But before we do, we're going to do two things. So, because someone said, hey, can you go through like every which way of this problem? We're going to do chain rule in a simpler way. But we have this form, so let's at least do this. So we have, and then, sorry, this is dx. So we have the integration of mbg divided by, so this term right here is going to be L naught minus h plus mb L naught. And I'll have to go back of like, did I make a mistake? Because why is this why is this term just a function of mass, but these terms aren't a function of mass? So yeah, that's boggling my mind right now. So I might have to go back and see if we made an error. Yeah, I think we made an error. Because look at this. Because we have max. Yeah, duh. So yeah, we made, yeah. Like anytime where your units don't match up, like throw some asterisks on the page and be like, whoa, you know what I mean? That's part of my videos too, is just like, you can't do everything right, but you can go back and figure out. See how this is a mass of B? Well, sure, you have some sort of proportion. Those units are going to cancel, but then you're still left with the mass. So if I said mass of X, sure, that's going to be LAX, but now I have to multiply by that original mass. So we apologize, but we have to go through this, you know what I mean, and do it again. So let's do that. Okay, so here's our, and you know what I mean, it should be easier to go through the second time. So here's our acceleration. We're going to say that's mBg, and then we're going to divide it by this term right here. And so, you know, should we still FOIL it through? The first term is going to be 1 MO, so it's just MO. And then the second term is going to be minus H divided by L naught times MO. Then the next term is going to be minus X divided by L naught MO. Okay, sweet. But then even right here, like we already know that we want to get it in terms of just X. So how do we get this in terms of just X? Well, what we would do is we would divide... oh, and see, I even made a mistake there. You know what I mean? If this is in the bottom, or did I do okay? I don't think so. Yeah, I think whatever I said right here, you can't just multiply by LO up top. And then, yeah, if I was going to do this, if I was going to multiply the bottom by L naught, I got to multiply the top by L naught, and it's got to be 1. Holy Toledo. So yes, if I wanted to do that, if I wanted to multiply through on the bottom by L naught divided by MO, then on top, I must multiply by L naught divided by MO. I mean, if I do that, then that's chill, and we can isolate this just as a function of X, because I just think it's going to make the integration just a little bit easier. It might not make any difference at all. So, so this top is going to be MBG L naught, and then I'm just going to do divided by MO. So that's going to be the top. Now the bottom is going to be, this first term is going to be L naught, minus, the second term is just going to be H, and then this next term is going to be just minus X. You know, I mean, that's what we were trying to do. Just get everything just with an X down here. Cool. Alright, so yeah, this top term, obviously, it's funky. Like, this could go downstairs, but we were just trying to isolate this as a constant. You know what I mean? So now we have something that's in the form of A, B minus X. And honestly, I haven't done enough integration to even, you know, think that this is necessary. But cool. So now we're going to say this whole thing is equal to the chain rule, dv dx, and then dx dt, which is, well, I guess I'll do it, dx dt. So that's going to be dv dx, and then this is going to be just velocity. And then we're going to get the dx component over here, and so we're going to have mbg L naught, I'm just going to do this, divided by m naught, L naught minus H minus X, and now we have dx is equal to v dv. And now we can integrate. Okay, hell yeah. So now we have something that's should be functionally correct. These masses cancel. This length cancels with this length. And then we have the acceleration. Yeah, that's the acceleration term. Sweet. And this term over here, so acceleration times, and again, remember that? It's meters per second squared times, well, in this case, we're integrating with position. So, yeah, I guess now I don't know. I mean, so this is masses cancel, length will cancel with these lengths, and we're left with gravity. And yeah, that's bizarre. You know, I mean, I guess chain rule is kind of interesting, but we get that. And then this side is going to be, we're going to have something like v squared. So this is going to be meters squared times second squared. So units will match. This is going to be meters squared second squared. It's just chain rule is just a little bit bizarre. Okay, so and then what I wanted to do is, like, let's say I just get it to here. I don't know. So yeah, maybe I just need to do I don't have enough skills to even, like, take this to Excel and make it make any sense at all. I honestly don't. But I do know that this is how you integrate. And so at least we have a check on reality from you know, I mean, our process through Excel, so we can get it. We can get an equation. This is going to give us an equation of velocity as a function of position. So then when we go to Excel, we can see if those line up and see if we didn't make any mistakes. But what I want to do right now is like, hey, let's say acceleration is dv dt, but it's also the chain rule, dv dx dx dt, and that's going to be dv dx, and then we have velocity here, and then we're saying acceleration is 10. So let's separate variables here. So this is going to be 10 dx is equal to dvv, or I'm sorry, we should make this v dv, and then I want to integrate. What this is going to do is going to give me a function of positions. Now we can say 10, and I can actually, get this 10 to the other side, which would probably make a little bit more sense. So we have dx is equal to 1/10 v dv. And so now when we integrate both sides, we get x as a function of velocity. and this is going to be 1/20th v squared plus a constant. So when velocity is 0, what's our position? Well, that's 0. So yeah, hell yeah. So this is for a falling object. And so, that's what I was doing. For a falling object, here's chain rule. Here's a position as a function of velocity. So let's see if it works. Because we know that a falling object at 5 meters will have a velocity of 10 meters per second. So yeah, I feel like I don't even have confidence in this, but you can rearrange this equation for velocity. Well, or what does this say? This says if we throw in 10 here, we're going to have 10 squared divided by 20, and hell yeah, that's 5. And we do know that at another 15 meters, at 20 meters, that's another full second. This is going to have a velocity of 20 meters per second. So at 20 squared, that's 400 divided by 20. Our position is 20. So hell yeah. Actually, I've never done that. That would be the simplest chain rule on planet Earth, and the most recognizable. Is just like, you have position as a function of velocity, but you also have velocity as a function of position if you rearrange. So we're gonna do 20x and then the square root of that. So this is velocity as a function of position. So now we can say, hey, 20 times I apologize. I'm doing this wrong. So this is an extra 15 meters, but this is a total of 20 meters down to this point. So if we say 20 times 20 square root of that, heck yeah, that's 20 meters per second. So now let's do it at a position of 5. 20 times 5 square root of 100 is 10, and now we have our velocity. So yeah, so that's hella, and so that's the same thing that we're going to be doing here. It's just that the integration sucks, and I need to take a break, and we're going to look in this book for our integration tables, and we're going to find one. So let me find it. This is Eschbach. This is Handbook of Engineering Fundamentals. Alright, hell yeah. So we're back, and it's just cool. I love this book because it doesn't give you, anything more or less than what you need. So, even right here, and in books like this, it'll say log is natural log. It's not, anything with log is going to be natural log. But we have this integral. We have integral of du of u is equal to just natural log of u. It's just like, no duh. And, but, so that's, if we have 1 over x, that's just natural log of x. But if we have this u du, then we can say that, that u is equal to L naught minus h minus x. And, if we differentiate this, how the hell? Yeah, if u is this, what is du? You know what I mean? No duh. So it's still du dx. You know what I mean? So you still have, hey, yeah, so u substitution is still saying, hey, this is the integral of, is this right? Is this right? Is du dx with u as a function of x. You know what I mean? So I think that's right. And this is going to be natural log of u as a function of x. I think written like this is what I'm trying to get at. Because right here, we have u as a function of x. Cool. And I want to say, what's du dx? Because if I do that... or no, I guess not. But yeah. I mean, you could say that. I think this will help. But I guess doing it this, now I get what we're doing. You know what I mean? Because if I'm saying this is u, this is still dx up here. So then I have to say, well, what's du dx? And so I do this. I say du dx is just differentiating. It's just going to be -1. So now I have this relationship that says du dx is equal to -1. So I think we can see what we're doing. We can just solve for dx and be like, hey, that's du divided by -1. So, and then we'll get it, we'll get it in this form. You know what I mean? So let's write it out. So we have, and this is just all a constant, so it'll be very useful just to write that out in front. So sorry for making this so tiny, but mbg L naught divided by m naught. So, and now we just have 1 up here, or we just have dx. So let's write it. So this is, yeah, well, I guess we'll just write it like this. So this is dx L minus hx. And we're going to say, hey, u is this. And then du is this, so we need to solve for dx. So we're going to say dx, bring that upstairs, this -1 downstairs. That's a negative du. So now if we do this and substitute this into dx, they're just equations, look at that. We're going to have mbg L naught divided by the initial mass of the chain, integration of negative du divided by u. So even right here, this negative sign is a constant. So we can just bring it outside and we can say, hey, negative this, and then we'll just do positive. So now we have something that's the integration of du, u, and now we can just solve this. You know what I mean? So this thing solves to natural log of u. And that's where the negative comes in. This other side goes to 1/2 v. Well, I guess we haven't solved it yet. So v dv. But cool. So now we're going to say negative mbg L naught divided by the initial mass of the chain. Natural log of u, and I'm going to do this in 2 steps because we can just throw this back in. So natural u is this. U is, and this I think has to be absolute value, right? If I'm not mistaken. So we have L naught minus h minus x. And this should always be a positive number anyway, because this is going to be 20 meters in length minus 10 meters minus, 10. So at natural log of 0, well, that's going to be negative infinity. That's the only place where it's... Oh, and then what's our constant of integration? You know what I mean? Obviously, this is where x equals to 0, and we're going to go all the way to x equals LA. So we're going to go from x equals 0 to x equals LA. And then we remember what LA was. LA, let's write it out. LA was just the length, the total length of the chain, minus h. Oh, I guess, well, yeah, the initial length. So, I guess, yeah, again, it's really nice to use these. So, this is going to be LA naught. So, yes, LA naught, yeah, that was the one for sure. Whole length of the chain is length initial minus h. That's going to be LA naught. So, hell yeah, that's going to be what we're integrating from, 0 to LA naught. So, we just did the integral, and then we can put these values on. X is equal to 0 to x is equal to LA naught. So, at LA naught, yeah, this becomes 0. And yeah, natural log of 0 blows up. So, man, I forget if we're gonna have an issue there, or you know what I mean. Like, damn it, I don't know enough about calculus. But anyway, so we're just gonna try like plug on, and we're gonna say this side is the integral of v dv. So that's 1/2 v squared plus a constant. Man, that's a bummer that we have a value of x where that thing doesn't exist. You know what I mean? But obviously, yeah. At here, we're gonna have no mass, so that's where we're assuming. Yeah, this point really doesn't. You know, that's nonsensical. That's a nonsensical point. But anyway, I don't know what the hell we're gonna do. And do we even need to have the constants of integration? Maybe we don't. You know what I mean? Yeah, damn it, I have no idea. But that's where we want to know where the velocity is. We want to know where the velocity is when this becomes LA. And then that's going to be, yeah, what the hell? So maybe I made an error in this, but I have no idea. So I'll have to go back and look at that, because obviously that's that this value doesn't exist at x is equal to LA naught. Alright, but let's say we didn't make a mistake. We still have to have a constant integration. And what this is going to say is when velocity at position x is equal to 0, you know, right when we're holding it, x is equal to 0, our velocity is equal to 0. So we throw in this 0, and then our velocity over here, this term is 0, this is 0, but we still have a constant of integration. So this constant of integration equals this side, like you know, our when position is 0, our velocity is supposed to be 0. So we need to have this constant balance this term. You know what I mean? So then when we get it to one side, it goes to 0. So I guess our constant of integration is just going to be negative mbg L naught divided by m naught natural log of L naught minus h. So it's just, you know, you don't use that term, but yeah, this is the, you know, there you go. So holy hell. So now I actually have to make sure, I'm just going to turn off the camera, double check I made, you know, what errors I made, and then try to clean this up. Alright, hell yeah. So I took a little break, and what we're going to do, it's always good just to start totally fresh and see if you can go through all those steps to get where you were. Because even though we just wrote hella, you know what I mean, we didn't do a whole lot. So we're going to say, hey, this is going to be our x position, so this is kind of what they do. And then when that at that x, here is our mass of A, and it's a function of s of x. I apologize. And so we're going to go back to F equals ma. We know the forces. We're gonna say, hey, we got some sort of mass at A as a function of x, tension in the line, and then definitely a bigger driving mass. And this is all just going to be like on a surface. And then this is mass of B, that doesn't change. So this can be just mass of B initial. And we have a driving force on it, the force of gravity. That's going to be the mass of B times G. This whole system, the total system for this mass is going to be both the masses together. So our only force, our net force, is that gravity. That's mbg. That's going to be equal to both masses together. So that's going to be ma, and I guess we have to say as a function of x, plus mb. Cool. And we're just saying that mass b is equal to mass b naught, initial, which is the same thing as those are synonymous. I don't have to do the naught every time. All right, so now we're saying that's the mass and this times acceleration. Okay, we rearrange for acceleration and say that the acceleration is mbg divided by max plus mb. You know what I mean? So just real quick, this is exactly what we did. And then hell yeah, we said this is equal to the chain rule. So that's dv dt. This is what acceleration is change in velocity, change in time. And then using the change rule, that's dv dx, dx dt. And we can see that this is dv dx times velocity. Cool. And then we separated variables. So we have mbg, you know what I mean, dx divided by ma as a function of x plus mb is equal to, I'm just going to switch these around, so we're going to go v dv. And it was at this point that we need the mass of A as a function of x. And so that's where we said that the initial mass is m naught. Cool. The initial length is L naught. And the initial mass, and then we were going to say this is mass of A initially is going to be a ratio between the length of A initial divided by the total length times you know, m the initial length, So we have that. And then from here we said that ma as a function of x, and I should write this as capital A if I'm going to do that all the way through. So ma as a function of x is equal to la, sorry about lowercasing that, la as a function of x divided by L naught. And then what is la at any given x? You know what I mean? So if we say x is 2 meters, for our problem where we're saying this is 10 and this is 10 meters, sorry, and this part of the chain is 10 kilograms, this part of the chain is 10 kilograms. So initially mass of B is 10 kilograms, and initially mass of A is 10 kilograms. The total mass m naught is 20 kilograms. So we say LA at any point is just, so let's do that. So we have LA of x at any point is just L naught minus that h, you know what I mean? Because that narrows us down to at least this length, but then minus x. Cool. So now we have minus x. And yeah, I think that's the way that I like doing this. Start x right here and go that way, and we know that x can only go up to LA naught. Hell yeah. All right, so now we write this in. Say ma of x is L naught minus h minus x divided by L naught. Now, for my next go around for this integration, I'm going to try to do little massaging as possible, because now we know how the u substitution works. And so now we can just throw this value in. And yeah, I really don't want to do too much else except let's get this. Let's do the, you know, let's say this is 1 minus h divided by L naught minus x divided by L naught. Let's at least do that. I think that is all we need to do. Well. And then we said max. I'm not doing all the steps. Sorry about that. So yeah, I'm making mistakes. So this is our ratio, because we're trying to find the mass of this chain. Well, it's the ratio of the length of the chain compared to the total length. And so that's where we get this term. But then this has to be times that 20 kilograms. You know, this is a dimensionless term. So that's the other thing. It's like, hey, if you're setting up an equation, you know, what are you doing right here? Well, you're just making a ratio. You're taking meters divided by meters. It's a ratio of the total length, and then this whatever the remainder length is up there. And then that's going to be times that initial 20 kilograms. So yeah, really apologize about making those. But I love making errors because then we can come back to them. So then this is going to be this times m naught. And so let's at least factor that all the way through. So we can say ma of x is equal to m naught minus h m naught L naught minus x m naught L naught. Cool. And then some people would put the x on the other side, whatever. It doesn't really matter. So this is what we're throwing into right there. So the only other term that we're going to have is plus mb. And then we can integrate. So let's do it. So we're going to have, I'm just going to rewrite this, mbg dx divided by m naught minus h m naught L naught, and yeah, we'll even write it in this order. Just, you know, like I wouldn't, but and I would switch those around too. It would just be visually easier. But we're gonna see if we can just like I said, less massaging, and just use the principles that we know. So we know that this is our u term. Our u term only has an x in it, so when we differentiate, we're just going to be left with a negative m naught L naught. Cool, I think we get that part. So this is going to be equal to v dv. So now we're going to integrate, and we're not going to put limits of integration yet. Oh, I think we have to, right? Isn't that the whole point? Holy Toledo. Yeah, that is the whole point, because you have to put limits of integration, like, right? Like, don't you? Like, honestly, don't you? Like, don't you have to say this is between 0 and LA naught? I don't know. And then but do we not have to? I lose my mind on calculus. I'm just like, well, what is just the generic equation? Isn't the generic equation just going to give us an x somewhere? We're going to get an x somewhere and a v somewhere. So let's not do this. And we're going to get an equation. Once we integrate, we're going to get an x. You know, we're going to get something like this, x, and it's just going to look horrendous. And that's going to equal to, you know, something v. So then we know our velocity at any x. So if we throw in LA naught, we should get our velocity. But that's where we ran into that issue again, where if we threw in LA naught right here, we totally struck out. So let's see just even right now if we strike out right here. So this is going to be 20 minus 10 times 20 divided by the L naught is 20. We have 20 meters of chain, 20 kilograms. Cool. And how are we doing so far? 10 minus, this is going to be 10 times 20 divided by 20. Cool. So this is 0, and now we have a positive. So maybe that's where I just messed up. I did not add the MB from, you know what I mean, I was catching my error. So now we have plus 10 kilograms. Yeah, so this, if we, and doesn't that make sense? Because we're saying, you know, going back to the acceleration equation, you know, we said that the acceleration equation is just right here. And so if we look at it, when max is 0, this goes to 0, and look, our acceleration is just gravity. We already figured that out. So even when we go to integrate, you know, we had this term that becomes our natural log. You know what I mean? So so now I feel more confident to put the limits of integration on, but we don't have to. Because essentially what we're going to get, it all comes down to the constant too. Because if we integrate this, we're going to then set when our velocity is equal to 0, our position is equal to 0, and then we're going to have some sort of constant of integration. So then at any point along this line that we put in our position of 10, then that's going to chisel us out a velocity. So now I feel hella confident. But yeah, I don't think these videos exist on the internet of someone that's just like, well, like, yeah, I know my calculus sucks. Like, this does not come just like super fast and easy. But I know how to not make algebra mistakes, and if I do, I can catch them. But the only way I can do that is if you watch this whole video and see how I did it in Excel, got numbers, so then I have something to check on reality, even just the logical stuff. So like one problem has like 10 mini problems in it. You know, the fact that, hey, when you run out of mass, this thing is just in free fall. Acceleration is just the velocity of that point. It doesn't matter. That's the other thing. It doesn't matter whether this velocity is going this way or wrapping around the corner. Any Pulley problem, You know what I mean? Everything in line with the path is the only thing you're concerned about. So the second this is free of the tube, the velocity of that point will just be in constant acceleration due to gravity. So, you know, if we find the velocity here and we want to know the velocity 1 second later, you know, that would be such a cool question for a test. Is like, hey, what's the velocity at A? And then have question B being like, okay, 1 second later, what's the velocity? You know what I mean? And then you'd be like, well, duh, it's just in free fall. All right, hell yeah. So now I'm feeling hella confident. So we know that we just have a dx term. And so we're going to say, hey, this is our u term downstairs. So we're going to say u is equal to m naught minus h, m naught divided by L naught. And again, like, hey, this is the proportion. It's h divided by L naught times that initial mass. That's what like downstairs is just a mass term. You know what I mean? These are the proportions of that mass. So yeah, anytime you got an equation, you know what I mean, something like, obviously you can stack it in a way that makes more sense. The way I have it stacked, it isn't very intuitive. Mass divided by L, you know what I mean, it might look, you know, like I'm not going to make mistakes, but okay, so let's do it. So we have this is x, m naught divided by L naught plus mb. All right, I didn't mess up any of the negatives. So now we're going to take this u and we're going to go du dx. So we just differentiate, and hell yeah, we have an x to the 1, so this goes x to the 0. You know what I mean? So yeah, like if you do dx, if you have, I think it's better if you do it. Y is equal to x. So then I want to go y as a function of x dx. So see how I do this? This is just simple integration. I throw that x in there. So I say d of this function x with respect to x, and we differentiate. So this is x to the 1. We know that when we differentiate, we lose a power, so it goes x to the 0. And then whatever this power was goes out in front. So we get 1x to the 0, and this just becomes, like this is 1, so we get 1 times 1 is 1. Hell yeah. But if we have, if we have what we have we have negative a constant x, and we're gonna differentiate that. So this is x to the 1, it goes x to the 0, the 1 comes down, and we still have negative 1c. So we have, and this becomes 1. So we get negative c. You know what I mean? So it's just the constant. So anyway, so that, but you know, stuff like that, like going over the basics of the easy stuff, will just strengthen. You know what I mean? Because there's no difference. It's actually harder to differentiate just x to the 1 compared to, oh, I'm differentiating d of x squared, you know, with respect to x. Well, hell yeah, that's going to be 2x. I don't know. I think that is way simpler than just integrating or differentiating just very basic, you know, things or constants or just an x value for differentiating. So hell yeah. So du dx, all these terms. This goes to 0. You know what I mean? Because I don't know why. But like obviously, duh. But no. Yeah, it'd be fascinating. It's like, yeah, I just said it. So this week I'm going to be thinking about that. Why don't have a logical explanation of why when we differentiate this, like what the hell is differentiating? Differentiating says when we change x by just a tiny amount. So x is going to go from 0. When x is 0, we got that, and it's going to go to 1. Now we have kind of this, you know what I mean? And then so that's going to be the change, you know what I mean? So it's going to be that, yeah. So we would start with this, and then we'd end with that, and then the difference between them is essentially just negative m naught L naught. Cool. So I don't know. I mean, I think that was a way to talk through what the hell we're doing. But anyway, so the differentiating du dx is just negative m naught L naught. But I swear the easiest things is just like, oh, I have no idea. All right, but hell, I'll find out now and then make videos. You know what I mean? I love like talking it out because you're just like, holy hell! Like no one taught me well enough that I don't even know why, if I differentiate a constant. Because, well, I do know this. If I differentiate u with respect to x, well, u has all these little things in it. So it's also, I could also differentiate this with respect to x, but there is no x. And then, so it's the summation of, yeah, so I'm doing 4 different differentiations. So I could do it like that, but I think we just need to move on. So we know the form here is going to be, we have the form integral of u, du up top and u downstairs. And this is going to give us natural log of u. So that's what we have. We solve this for dx, and we say dx upstairs. And then we got to get the other stuff. We need to get dx alone. So we need to take this up that way, and then this stuff over. So we go, so this is going to be negative du times, and then the L naught goes upstairs, the M naught comes downstairs. So this is L naught divided by M naught. And we might not write it like this, but we do like this. It's going to be negative L naught divided by M naught du. Cool. So when we replace dx, we have to replace it with this. So let's do that. So we're going to have mbg. We're going to replace it with this. So now we have negative L naught M naught times du. And then downstairs we just have u now. Hell yeah. And we can see that this all is a constant that can go out front of the integral. You know what I mean? So if we're integrating like this, this can go on the other side. And then, so we'll do that in a second. And then we have the integration of v dv. So we don't have a lot of room, and I should give myself some more. But I think we got this. So we're going to have negative, like this doesn't change. It's just going to be a constant outside this. So we have negative, how do I want to do this? And are the units on this right? I swear. Who knows? Yeah, we'll see. Yeah, I thought this was right. Yeah, M naught, L naught. And then if we get the dx over here, this goes L naught divided by M naught. Yep, perfect. And then we throw this in for dx, and that's what we did. Cool, well, let's run with it. So we have negative g L naught. We have mb divided by M naught. So we do have maybe that proportion. And now we have the natural log of u, which is, oh, I didn't leave myself room, which is this. M naught minus h, M naught divided by L naught minus x, M naught divided by L naught plus mb. Damn, so I think I'm going to get another sheet of paper, and then we integrate this side, and this is going to be 1/2 v squared, and now we have a constant. So when we say, when x is equal to 0, our velocity is equal to 0, so that means, let's do our constant though. So our constant is going to just equal this side. This got to balance, right? When this is 0 and this is 0, this equation has to be valid. And so whatever's left on this side, which is negative g L naught mb divided by M naught natural log, and then this is 0, you know what I mean, so we don't include that, but we still have M naught minus h, M naught divided by L naught plus mb. Now, when I go to rewrite this, I might put the h and the L naught together, and then just so it just visually makes a little bit more sense. So I'm going to rewrite this on a new sheet of paper, so I'm going to catch on the flip side. Alright, hell yeah. So we're back, and I just thought of something, because it's like, I feel like I don't even know how integration works, because, you know, let's say we're in free fall, and our acceleration is just, so here's our acceleration, here's our time graph, and you know, it's real simple. Times in seconds, acceleration. This side is in meters per second squared. The area it gives us a value in meters per second. That's velocity. And when acceleration is constant, it's cool like that. It's just constant. But you could, it's like this is where the proofs come in. If you do have something where, hey, it looks like this, now it's like, well, our acceleration is going to vary, but there's some point where it becomes average. And I just don't know enough about, like, well, no duh, because even with that initial acceleration equation where we have acceleration is mg max plus mb, like, I get what we're doing to find an equation for velocity, but couldn't I just integrate over this distance to get an average acceleration? That's what I'm kind of confused about. It's like I want to walk up to a problem and be like, well, let's just figure out what the average acceleration, because that's what we did in Excel. We saw the acceleration there was 5 meters per second and 10 meters per second. We know that the average isn't 7.5, and we think the average is more, because I think we think the average is more over here. Or is it less? Because let's use at least what we know from chain rule, is that if we have 10 for our acceleration, and that's going to equal dv dt, we're going to do the chain rule, dv dx, and then dx dt, and we're going to say this is dv dx times v, and then just, separate variables. This is 10 dx is equal to v dv, and integrate, well, and then we can get the 10 down here. So it would be the integration of dx is equal to negative 10 square root, integration of v dv. And if we do that, we get an equation for position is going to be 1/10, it's going to be 1/20th v squared. So this is going to give us, I need to pause the camera. Oh, my bad. I'm going down a wrong route. But let's stick on this topic because it's kind of interesting. Because we have the kinematic equations that say, and what are we trying to? I guess we have the kinematic equation that says velocity is going to be our average acceleration. So we can say that this is going to be average acceleration times time plus our initial velocity. So hell yeah. So if we already know our velocity, oh damn it, we just don't know the time factor on that either. Oh yeah, this is fascinating. Just to get like a no-duh approach. Didn't we say that the halfway point was like an acceleration of 6.6? Well, yeah, so we're going to be slowly accelerating, and then all our acceleration happens right at the end. With that 10. So if our graph looks like this is 5 and this is 10, halfway is hella not the average. You have to go like, so if you're taking this as your area, 5 divided by 10, hey, your center of mass is going to be like right here. So your average velocity for this problem is only like 7 meters per second and not and not halfway between 5 and 10. It's not 7.5. It's closer to 7 and maybe even less than 7.5. So yeah, that's a side deal. So hell yeah. So we did integrate this, and we have an equation for position. We only have one position in here, and then we can find the velocity. So right now we could just do that without cleaning it up. And I think if you ever get to this point, you should just do that. So let's throw in values. So we got negative 10, L naught is 20, 20, and then we have mass of B is 10 kilograms divided by 20. So this is 10 divided by 20. We have natural log, and this is why we just made a problem with simple parameters. Is 20 minus h is going to be 10 divided by 20 times 20. And then you can just see that, hell yeah, this is just 10. And then, hey, well, what's this? This is just negative 100. So, negative 100. Cool. So, yeah, keep on going. And now we have negative, and then when x is 10 meters, so we have, again, 10 divided by 20 times 20. So this is just going to be 10 again. And then plus 10. Cool. So we have, and I guess these are negatives, you know. So we have negative 10, negative 10, 20. And then so we're just left with positive 10 here. And that's what we were hoping for. You know what I mean? You know, we just, so I'm just going to say positive 10 on this. We have natural log of 10. And sweet. And this is the natural log. It's not the log base 10. And even your calculator, it's just like, man, I don't want to rack my brain of like, could I just guess? What the hell is a natural log of 10? I'm just going to guess. For whatever reason, I think it's like 2.3. Yeah, 2.3. Hell yeah. Whew. But that was a total guess. You know what I mean? That wasn't using solid. I was using logic and guessing. So there you go. All right. So now that's going to be equal to. So we have what we don't know. So we have 1/2, and we just don't know what v is. You know, we're saying at the position of 10, we want to know what our velocity is. But now we have to minus this side, and this is going to be minus 10 times 20. Difference between the masses, 10 divided by 20. And so look at this. This is going to be negative 100 again. Cool. We have natural log of 20 minus 10 divided by 20 times 20. Sweet. So again, this is just negative 10. And plus 10. So now this term is going to be, this negative 10, this term is going to be natural log of 20. And I think natural log of 20, what is that, got to be like 7? You know what I mean? Let me guess. Natural log of 20. Oh, I have, yeah, duh. No kidding. I don't know why I messed that up. Because it's e, so it's if we have 2 to the 2.7, that's 6, and 3 to the 2.7, that's 19. Well, isn't that natural log of 20? That's, oh, well, yeah, natural log of 20 is going to be 3 point something. So natural log of 20, or I guess it's going to be just less. Oh, yeah, because it's 3 point, it's 3 to the 2.7172 or something. No, what's e? So alpha e to the 1, 2.718. So 3 to the 2.718. Wait, 3 to the alpha e to the 1. Well, why is that less than 20? You know what I mean? And then so why is natural log of 20 less than 3? Yeah. So anyway, I guess I just don't know my natural logs very well, but it doesn't matter. You know what I mean? You have your calculator do it for you. Holy Toledo. Okay, so we have negative 10 crosses out with that 10, and we got natural log of 20. So sweet. So we have, natural log of 20. Right here, we're going to have natural log of 10. And so cleaned up, we have negative 100. Natural log of 10 equals 1/2 v squared minus 100 natural log of 20. Cool. So we're going to have negative 100 natural log of 10, and then we're going to add it to 100 natural log of 20. And sweet, we get a positive number. Well, we're gonna multiply. So I guess we have 69.3147 is equal to 1/2 v squared. So we're gonna multiply that by 2, and so we're gonna say, multiply this by 2, and then take the square root of it. So v is going to be the square root of 2 times 69.3147. And can we do this in our head? It's the square root of 140. No one knows what that is, but it's bigger than 10. And 144 is less than 12. Hell yeah. And didn't we say it's going to be like 1.77? You know what I mean? From what I remember. And for sure. So now we're doing things right. 2 times, what was that? What was that number? I'm I'm going to store that. Store that is, I don't know, just alpha w. Or store it, whoop. Alright, hell yeah, we're back. So we're going to store this value as alpha w in our calculator. And then we're going to do the square root. Well, I guess I can just pull it up. So yeah, we'll do it, right? So we're going to do this just so you can see. So it's 2 times the, whoa. Now, I don't know what's up. So alpha w is that, and we're going to go square root of 2 alpha w. Alright, booyah. And we get our velocity is 11.77 meters per second. And I got something to think about, you know what I mean? Just at the end of this, I was trying to come up with some scenarios of like, well, what the hell is just the average velocity? Why can't I answer that question right now? It drives me crazy. If I know the final velocity, you know what I mean? I know the change in velocity. I would have to go back to Excel to figure out the change in time. That's the thing, is acceleration is change in velocity, change in time. That's the only thing, is like I don't know how long this is going to take, because I don't have that equation. I have an equation of velocity as a function of position. Now I could plot those, but I don't have velocity as a function. I don't have it as a function of time. So I don't know at what time did that take to release. So I definitely want to come back and answer that question. Let's see. So we did it, and we used natural logs. I'm going to rewrite this because we can clean this up. And the reason we can is we can get this has a natural log and that has a natural log. We're going to bring this is subtracted over on this side of the equation. We're going to add it to this side of the equation. So then we're going to have something minus, so this is going to be our something, positive something. It has a natural log in it. And then we're going to subtract it from this natural log. Like, hey, look at all this. At first, you know, like, hey, those things outside can go outside of that. But now we'll have this natural log of this minus the natural log of that. And anytime you have that, that's the same thing. So if you have the natural log of A minus the natural log of B, then you just stack them. You know what I mean? It's like saying the natural log, and then you throw A up here, and then you divide it by B. And then you just have, you have this. So you have the natural log of A divided by B. So we're going to do that just to get a nice crispy equation. And then we'll multiply by 2 and take the square root of it. So we'll have velocity as a function of position. Alright, hell yeah. Alright, sweet. So we have that rewritten, and I guess we're just going to write it again. We're going to get this over here. So we're going to have, and then factor out this G L naught MB divided by M naught. Cool. And so that's what we factor out. And now we're going to have, I guess we can just do it all in one step actually. So now we're going to have the natural, this is going to be the positive one over here. So we have the this goes on top, M naught minus H L naught M naught plus MB divided by this. So now we have M naught minus H L naught M naught minus X divided by L naught M naught plus MB. Alright, sweet. And this is just a general equation. You know what I mean? So, and then, holy Toledo. So we're going to multiply this by 2 and then take the square root of it. You know what I mean? Because obviously this is equal to 1/2 v squared, but I don't want to rewrite it again, so I'm just going to say this is equal to velocity, and then we're going to take the square root of it. So there you go. So now we have an equation of velocity as a function of position. So that's cool. Now we know our velocity at any point along here. And basically the natural logs say is well, I mean, I guess I just don't want to get into it, but like if you were going to do, natural logs are the only equation that can peter out at just like any value. You know what I mean? Like if you had an x squared, I mean, even if you had like a I guess in the vertical, I mean, if you turned a logarithm vertical, you could do this, and then it would peter out in a vertical line. You know what I mean? But an x squared will never do that. It'll just keep going. You know what I mean? So I guess here, isn't this like the square root of x? Like if you had the square root of x, you know, it'll soften out. Like it won't go that direction very much, but it'll still go that direction to infinity as it goes to this direction to hella infinity. You know what I mean? But natural logs, you can get them to stop at any value. So that is kind of the usefulness of them. And it's depending on how you use them, because even natural logs in their general form will go to negative infinity, and 2 they will go to positive infinity. But you can get them where they kind of cap off at a certain. So that is kind of cool. One cool property about using natural logs. Okay, so but they just want, with what velocity will the end of the chain slip out of the tube? So we're going to throw in LA naught, you know what I mean, LA naught. So when we do that, then we'll see what cancels. Sweet. So let's do that. So we're going to have velocity is equal to 2g L naught mb m naught natural log. Now this upstairs is going to be the same. M naught minus H L naught M naught plus MB. But the downstairs will be M naught minus H L naught M naught minus, this is L A naught divided by L naught. Well, yeah, when x is at this full distance of LA naught, yeah, for sure, that works. M naught plus MB. Oh, but I see where we really can't cancel anything. But what we have to say is that, yeah, if this is the total length, this LA naught is equal to, so LA naught is equal to the total length minus H. So that's all we had to do was just throw in that value. You know what I mean? It's just interesting how you can label something, but then you'll just go back to the original problem. It's just like, hey, we have a length, we have a chain of length L. Sweet, this is L naught, and then we have a height H. So in our equation, we have, like the only things that we have are H and L naught. And then even if we go back and say, you know, even for our mass of B, we can get this mass in terms of just L naught and H, and just the total mass. So yeah, and I guess it doesn't say that, hey, it has a total mass, but obviously that's a given. Okay, so let's do that. So we're gonna replace this LA naught with this, and we should be able to cancel. Let's just do it. We're not gonna write the whole thing. So we're gonna go M naught minus H divided by L naught M naught. Now we're gonna say, hey, this term is equal to this. So we're gonna have a minus M naught, because it's gonna be L naught divided by L naught times M naught. So it's gonna be 1 times M naught, and we still have the minus sign. But then this, you know, we're taking this and putting L naught minus H. So we have minus L naught, but then we got plus H. So I guess I'm doing 2 steps. Sorry for doing too many steps at once. But now we're going to have plus H divided by L naught. H divided by L naught times M naught. And look right here. So we already have one of those, and then we have one of those. We have one of these, and we have one of these. So now we're just left with MB on the bottom. So cool. So we can say the velocity 2g L naught mb divided by m naught, natural log of the top, the initial mass of the chain minus h, the initial length, initial mass plus mass of the b portion of the chain divided by the mass of the b portion of the chain. Alright, sweet. And I think we can even get this just a little simpler. And so I'm going to do that on my own, and if I can, I will let you know. So anyway, I'm going to take a little break and see if I can simplify. I'm never going to look at the problem. Hell no. If I did a mistake, who cares? You know what I mean? We're just working through the fundamentals. But we already did a problem where we checked our answer. And we could even check our answer right here just a lot faster. We got 2 times 10 times 20. And then we got 10 divided by 20. We have natural log of the upstairs is going to be 20 minus 10 divided by 20 times 20 plus 10. The downstairs is going to be 10. Cool. And I think I just either put it in the calculator wrong or just made a huge error. So let's do this. Let's do the top. It's going to be 20 minus this is going to be 1/2 of 20, so it's minus 10. So we're going to have, oh, damn it. So we have 20 minus 10 plus 10. Cool, so we're going to have, and this is going to be divided by 10. So divided by 10. So we have natural log of 2. Natural log of 2, and now we're going to multiply that by this ratio, which is 10 divided by 20, so that's 1/2, times 0.5, and then times the total length is 20. And then times gravity is 10, and then times, no duh. You know, I didn't take the square root of everything. Holy Toledo. So that was it. You know what I mean? So if we do that, and then we got to multiply by 2, and then take the square root of it. Yeah, so we did at 138, that popped up. I didn't have check on reality on that one. So when we made the error, that 138 popped up, and hell yeah. So we get 11.7. So this equation jives. And I'm going to take a little break and see if I can simplify this down. But I mean, basically what I want to do, I want to get a velocity as just a function of what? I want to get it as a function of L naught, the length of the chain. I like saying L naught just because it makes mental sense to me. And then I want it as a function of H. Cool, that H doesn't change. And then I think I'm going to have it as a functional of the initial total mass, which I'm calling M naught. And so there you go. So I think I can get everything else as a function. So even this MB, I think MB I can write as a function of L naught, H, and M naught. Sweet. So let me do that and catch you on the flip side. All right, hell yeah. So I take a big break, and we're going to keep trucking with this problem. There's so many more questions that we can answer. We can do this. We can say the derivative of the velocity is dx dt. Separate variables again, and then we can get an equation of position as a function of time. You know what I mean? Okay, but the first things first, we want to get this equation, let's see, just in terms of h and the total length. So, you know, we have this term, and isn't that what we have? I got to see. Didn't we already? Oh, did we already do that? Yeah, I totally forgot that. Hell yeah, we already did that. We already changed LA naught, and now we do have a function of velocity as a function of the initial length, the initial mass, and oh yeah, but we wanted to see if we could get the mass of B as a function of just the initial mass. So let's do that. So we know that the total mass is m naught. We know that the initial total length is L naught, and we know that the length associated with the mass of B is going to be a ratio of H divided by L naught times that total mass. So cool. So this is mass of B. So anywhere where we have mass of B, we can just replace it with this. Cool. Yeah, well, let's do that. So this would become H divided by L naught, and then times mass naught. So we're going to cancel these out. So this just becomes H divided by L naught. Hell yeah. And then over here, let's see what we got. So we're going to have downstairs, this is going to be h divided by L naught M naught. And then upstairs, this is going to be h divided by L naught M naught. So maybe we actually do want to divide this through. So this first term is going to be m divided by M naught. Cool, so this first term is just h divided by L naught. This second term is going to be h divided by L naught divided by h divided by L naught. That's the same thing as multiplying by the reciprocal, so we would have L naught divided by h, so those cancel. Either way you can look at it, those cancel. And so this is just -1. So we have -1. Cool. And then here, here, oh, and if we, if we look at this, we have h divided by L naught M naught plus h divided by L naught M naught. So those are just going to cancel. So cool. So then we'll just have this term divided by that term, and we're done. So we have h divided by L naught. Sweet. So that's it, and we don't even have that. So this whole term in here just becomes h divided by L naught. This becomes h divided by L naught. And yeah, our velocity term gets hella simple. Before I write it, let's just make sure it's right. So square root 2 times 10 times 20. And even right here, holy Toledo, these L naughts are going to cancel. So we're going to have 2gh, and I guess I don't want to write it until I know it's correct. So we have the square root of 2 times 10. Now we just have times h, so that's going to be times 10. Natural log. This whole thing, holy Toledo, it just becomes h divided by L naught. That's amazing. That's cool. Yep, and that's right. Well, did we do that right? This is going to be M naught divided by h divided by L naught. See, I think I'm flipped on this. Yeah. Because what's the natural log of 0.5? Yeah, because this would be a negative number if that's the case. And yeah, since I know about natural logs typically, always have to be positive. I mean, they have to be positive numbers. You have to have natural log of a number greater than 1. Natural log of 1 is 0. Natural log of 2 is a positive number. So this ratio, so I can see my mistake, is that we did M naught divided by M naught, but this is 1 divided by h divided by L naught. So we're going to flip it. So this is L naught divided by h. Heck yeah. And then here we're good to go, because M of b is just h divided by L naught, so sweet, we're good there. Okay, let's see if I wrote this right now. So we have times natural log of L naught divided by h, and we'll see if this jives. So we got 2 times 10 times 10, natural log of natural log of 20 divided by 10. And and the square root of that, obviously. Duh, I always forget that. So yeah, this is that's our answer. So it's just super simple. So even after all that, but I'm glad I did it the way I did it, just because it was the only way to mentally figure out, what are the proportions of mass of A and then mass of B. Else it would have just get lost. Alright, but before we go on, or maybe we should do an analysis first, but remember how this equation of V is a function of x, and then we just evaluated it at x. So we also want to, at some point simplify this down, because we're going to integrate it again. But right here, so we have our velocity, once the chain leaves, is going to be 11.77 meters per second. And then I'm going to go back to my equation for acceleration. Let's see if I can find it. And let's rewrite this equation for acceleration. So we had acceleration is just, what was it? It was mass of B times G divided by MA plus MB. Because even in this form, you can't see it no more. So we basically start with the force is equal to mass times acceleration. What do we have? We have these two masses connected. The only driving force is mBg. So you say this is mBg, and then this is the mass that we're interested in. But we need to get an equation for acceleration. So we have to have this force mgb divided by the total mass, which is ma plus mb. Sweet, and then that's the equation for acceleration. But we know mass of A is a function of the length, and yeah, this is tripping me out, but let's go back to say, hey, at some point this is going to be at x, and then we have a mass A of x, and that's associated with the length LA of x. And so I definitely want to go back and do this, just so I'm set on it, because we were saying that LA as a function of x is equal to the total length, got to start there, minus h, cool, so that leaves this section left, and now we're going to say it's minus x. Okay, hell yeah, and this jives because this is just a function of the initial length, h, and then this variable x, cool, and then we're going to say if we know LAX, then we know the mass of A as a function of x is equal to LAX divided by the total length, or the total initial length, times the mass initial. So that's going to be the ratio. Because, if we have this total length, and then we're just taking that section of it, that's going to be the ratio of that section compared to the total length. And so that would give us, times the weight of the total, that would give us the weight of that section. Cool. So, and then, throwing this together, this goes into there. So we have L naught minus H minus X divided by L naught times M naught. And, I think we want to kind of multiply these together. So we have, this is where we get M naught minus H divided by L naught M naught, and then minus X divided by L naught M naught. Yeah, cool. So, and maybe you don't want it written like that. You could just factor out the initial mass and have it 1 minus H divided by L naught minus X divided by L naught. Okay, but yeah, now this is a true equation for acceleration. This is kind of where we started. So we have mBg divided by the initial mass, 1 minus H L naught minus X L naught. Cool. So this is the acceleration at any given x. So when x is equal to 0, we have the mass is 1 minus H divided by L naught. And you can see if these are a perfect ratio, like for our problem, I'm going to say this is 10 meters, this is 10 meters, this is 10 kilograms, and this is 10 kilograms, but all those could vary, right? but then that's going to be a ratio of 10 divided by 20, and you're going to have a half here. So 1 minus a half is a half, and then that just says, hey, the total. Whoa! So I apologize. See, this is where I mess up. This is the mass of A. So then we have to say plus mass of B. Sorry about that. But now this is the equation. But if we throw in x is equal to 0, this will give us half the weight. If these two lengths are the same. So we're going to do that, half this length, and then we're going to add it to MB. And didn't we just say what the hell MB was? MB was equal to H divided by L naught times M naught. Cool, so let's do that. So let's cross this out and say this is h divided by L naught m naught. And now we can see that we already have a negative. So right off the bat, we could have really simplified that. And I didn't catch that. So now we have acceleration is, and up top, you know what I mean? How many times could I have simplified this? Because now up top, this is going to be h divided by L naught m naught. You know what I mean? So like the m naughts cancel, the initial mass cancels everywhere for the acceleration. Yeah, that's fascinating. It's fascinating that we're just dealing with ratios now. You know what I mean? That's what this equation basically says. It says it doesn't really matter what the initial mass is at all. And that was funny because it never gave a unit for the initial mass, and that's why. Because you can get an equation. Well, I don't know. Like here. Wait. What was our equation in the end? Yeah, our equation in the end has nothing to do with the initial mass. That's fascinating. You know what I mean? Right? Yeah. I did not notice that. But right off the bat, everything cancels with acceleration. And so here you have h divided by L naught. Well, all the masses cancel. We already did that. The MBs turn into h divided by L naught m naught, and then all the m naughts cancel. So now, and then this, like these two cancel. This is a plus h L naught, and this is a minus h L naught. So now downstairs we're just left with minus 1x divided by L naught. And then upstairs, we're just left with, I think we're still left with this ratio, 1 minus x divided by L naught. And then upstairs, we're left with, so let's write this. So upstairs, we're left with GH divided by L naught, 1 minus x L naught. Cool. So now let's see if this is our acceleration that we should come up with. So we have 10 times 10 divided by, this was going to be 20, and then 1 minus, and I guess, well, we have to figure out the acceleration at a given point. At x is equal to 0, this is just 0. So let's try that one first. And we get 5, hell yeah. And now let's try the halfway point. So we're going to go minus x is 5 divided by 20, and this should give us 6.6. Remember all those values that we were getting, and then if you say if this is 7.5 divided by 20, you get acceleration of 8. And then if you say it's just 10 divided by 20, hell yeah, you get the acceleration of 10. So sweet. So I'm actually going to that really chisels it down. I'm going to rewrite this velocity. So we have velocity is the square root of 2gh natural log L naught h. And then we have this. The acceleration is gh divided by L naught 1 minus x divided by L naught. And like this isn't even the simplest way. Obviously, you can factor this. This is going to be L naught minus x. So yeah, that's way simpler. So we got GH L naught minus x. Yeah, really simple. So now this is the acceleration at any given point. The reason that I'm doing this is just to get better, but also, we definitely want this graph that says, hey, this is our acceleration and this is our position. So this is our position in meters. This is our acceleration in meters per second squared. And we just say at x is equal to 0, we already have an acceleration of 5. And then we're going to go up, but we're going to go up to acceleration at 10 right at the end. But, you know what I mean? And I wish I drew my graph better, but 5, 6, 7, 8, 9, 10, let's say. And so even at halfway, and we're going to say this is to there, right? Like this is the 10 meters all the way across. This is going to be that point. This is the start point. And so at this point we have 10, but at this point we only have 6. At this point we have 5. So like right here, look at this. So we go to there. At this point we have 8. You know, it's not totally drawn to scale, but we got something like this. You know what I mean? So this is going to be the acceleration. Now, what I wanted to do is just be like, well, you know, isn't there just like an average value? You know what I mean? It's not going to be, if this was linear, like let's do the linear approximation. If this was linear, our acceleration would be right at that 7.5, right totally in the middle between 5 and 10. Our acceleration average would be 7.5, but it's not. It's much less because of this curve. So that's what we're going to find out, and we can already find that out. Like, we can already figure out where the average acceleration is, even from the integration that we already did, because we said, hey, we know what the velocity is. This is the velocity at the very end. You know what I mean? But this is the velocity at the very end, and we found that to be 11.77 meters per second. So then we can say that we have this equation for average acceleration is change in velocity, change in time. Now, as long as acceleration is average, this is a legit equation. You got 3 things. We can write it 3 ways. So we can write change in velocity is average acceleration times change in time, or we can write change in time is change in velocity divided by average acceleration. Okay, so but we don't know 2 things. We know what the change in velocity is. We're going to basically go from here to here. We're going to change our velocity by 11.77 meters per second. But we do not know our change in time, and we do not know our average acceleration. So this is where I'm going to use the kinematic equations kind of maybe in a different way, in like reversed. Because typically with the kinematic equations, it's like, hey, if I'm given an average velocity, a constant velocity, I can say that's equal to dv dt, and then I can separate variables and integrate. And so if I do that, I shouldn't have done it that way, but I get dv is equal to acceleration dt, and then I integrate and I get velocity is equal to the average acceleration times t. Now you could just memorize this, because the next one is going to be position is 1/2 a t squared plus the initial velocity plus the initial position. For our problem, you know, after we integrate, this is going to be the initial velocity, but our initial velocity is 0, you know what I mean, when we start. Okay, so here's an equation for velocity, and this is 100% accurate, you know what I mean, but we still, we know, and at the time here, at the time when it releases, you know, we still don't know that. We still don't know average velocity, I mean the average acceleration, but we do know the velocity at that point, you know what I mean? So, I mean, we're in the same boat that we started with. We know this. We know change in velocity, but we don't know the time or the average acceleration. So we integrate again, and so we say v is equal to dx dt. So that's going to be average acceleration t, and then separate variables. So we're going to have dx is equal to average acceleration t dt, and then so we're going to integrate. And now we get an equation for x is going to be 1/2 that average acceleration t squared. We didn't have any initial velocity, but we might have an initial position, but we're saying this is x is equal to 0. So this is our equation. Cool. And we could have just known that, you know, from the kinematics. But it is good to integrate them, because then you can never go wrong. And so right here, well, 2 things. This is going to be our velocity. So we at least know that. Let's write it in. So we have 11.77 meters per second is equal to our average acceleration times time at this point. So at this point when the chain leaves, that's going to be the t, you know, for our equations. And right here, we can say, hey, when is this position going to happen? Well, for our problem that, you know, we made it simple, is going to be 10 meters is equal to 1/2 a t squared. So now we have 2 equations, 2 unknowns. Here's 1 equation, here's 2 equations. We don't know average acceleration, and we don't know the time, you know what I mean, at 10 meters, which is the same thing as the time at when the velocity is 11.7. So these are what relate, since we know both those two terms from our first integration, because what we did is we took acceleration and saw that it was some function of position, and then we said, well, we can do the chain rule, so that's going to be dv dx, cool, and then times velocity. And then we can, get the dx over here and then integrate both sides. Hell yeah. So then we got basically a function of v as a function of x. And so that's what we got. And we threw our x value in. So that's what this says. V and x. Well, we know what our v is from that equation, and we know what our x was. You know what I mean? So that's what we did. And now we're kind of working backwards to find the average acceleration. So one of these we have to solve for. Well, let's solve for. Well, I mean, we want average acceleration, so let's solve for t. So we're going to say t is equal to 11.77 divided by a. And I don't think I have that velocity in my calculator, but we could store it. Isn't it alpha w? No, times 2 square root of that. So yeah, I'm going to store my velocity. This is alpha w in my calculator. This will just be 10. Okay, so now I'm going to shove this t into here, and now we can solve for a. So in here we got 10 is equal to 1/2 a average acceleration. And I'm just going to say this is, this is stored as w. So I'm just going to say that's w squared divided by a squared. Cool. One of these a's cancel one of those. And then, so we're going to have an a downstairs. We're going to bring it upstairs. So we're going to have 10. Oh, well, what do we want to solve for? We just want to solve for this a. So let's get a upstairs and then bring the 10 downstairs. So that's going to be 1 divided by 20. And we still have our velocity, this 11.77 squared. So I guess I should have wrote 11.77. That would have been visually better. But here you go. So here's our average velocity, and let's see if it works. So we have alpha w squared divided by 20. And yeah, that's what we thought. It's going to be less than 7.5, and we found that it's 5.6. It's going to be right there. And even visually, that looks about right. And so our average velocity is 6.93. I'm going to store that as alpha a. And I'm not going to store it as alpha theta just in case. Cool. So now we found our average velocity for the problem if acceleration was constant. I mean, no. Sorry, we found our average acceleration for the problem if that acceleration was constant. If we just had a constant change in velocity from 0 meters per second up to 11, that's what it will look like. But we see that a lot of our acceleration, a lot of our change in velocity happens at the end. We don't see very much change in velocity at all until this thing, like bleeds weight, and then all of a sudden, hell yeah, you got a bigger driving force on a less weight, and then you see a bigger change in velocity. But again, the key point of this is this right here. This line right here is where the change in velocity is 10. For every 1 second, this changes velocity of 10 meters per second. And I guess this is an acceleration curve. Oh yeah, that's fascinating. Oh yeah, so it's not going to be a tangent. I don't know what the hell I'm even thinking. But at that point, your acceleration is going to go like this, and then just go like that. You're going to have constant acceleration. So yeah, my bad. Yeah, that was kind of interesting. But yeah, it's going to go up to 10, and then it's going to be a discontinuous line, because now that position A is just going to be in free fall. Sweet. And I think that's true. I don't think if you have a chain that's in free fall and then that'd be fascinating. If you have a chain in free fall and then one section hits the ground, I think something bizarre happens. That's just me. I think you're taking mass out of the system, And so that's a problem I'm going to analyze. Like, obviously, if you just have a falling chain, it's going to fall at the acceleration of gravity. But then once that chain, the bottom of the chain hits the ground, I swear something funny happens where you could have a more rapid collapse, I'm thinking. But I don't want to get into that. Okay, but hell yeah, this is kind of what we wanted to do. We just wanted to find, like, look at this graph. And because this graph, this graph is not useful. This is what we did. We saw that acceleration, our acceleration was a function. So here's our acceleration. It is a function of position. We use the chain rule to integrate, and then look what we do. So if I found the area under this curve, what's the units on this? It's in meters per second squared. But now my units down here is distance. So this actual area, if this was just like a square block of meters per second squared and meters, we would multiply those two units together. Meters per second squared times meters, and this gives us meters squared second squared. And this is why when we integrate with the chain rule, like this right here is velocity squared. It's meters per second and it's squared. Those are the units on it. And then we just have a 1/2, and I guess I get it since we're starting at 0 and then ending at some sort of max velocity. But other than that, I don't know how to officially explain that 1/2 from that side. But I think that officially explains it. But I don't know, just from this graph. I mean, just if this is my acceleration graph, and I'm saying what's the area under the curve, because we did that. We found that velocity was a function of x. And then, yeah, so we got this. So here's our velocity as a function of x. And, yep. Oh, but yeah, this was kind of a velocity squared. So this was, if you want to say the units are squared, yeah, this was my velocity squared as a function of x. All right, but I think there's a couple more questions that I want to answer from here. And one, okay, so now we can clean this up. So that's the next. I'm going to grab a new sheet of paper, rewrite this, and then we have to clean this up. This velocity is a function of x, because we have to integrate it again, and we don't want it to be hella complex. All right, hell yeah. Okay, so we have this rewritten, and basically all we need to change is this mass of b. This is going to be the ratio of h compared to the total length, or the length initial, times the, the mass initial. So we can just say, hey, look at this. This is the MOs will cancel if we throw in this for MB, and then this is just going to be h divided by L naught. The L naught will cancel with this, so this is just 2GH. So yeah, remember that from before. So this is 2GH. We have natural log, and then, so here, let's throw in the top one. This is going to be just h divided by L m naught, and that's going to cancel this one. So up top, we just have this term, so keep that in mind. Downstairs, we're going to have h divided by L m naught here. That's going to cancel this one. So those two will cancel, and now this m naught is going to cancel everywhere. So now we're going to have a 1 divided by 1 minus x divided by L naught. So let's write that. So we're going to have 1 divided by 1 minus x L naught. And you could multiply L naught top and bottom. So that'll kind of make this a little bit more better looking. So if we multiply the bottom by L naught and the top by L naught, all we've done is multiply by a unit of 1, but this just can be visually more pleasing. So we have L naught divided by L naught minus x. And then it frees up that x term. So if we use the u substitution, now we just have a negative and no other constants to deal with. So that's it. This whole thing is just L naught divided by, and then we'll double check it. So now we have our equation for v is going to be 2gh natural log of L naught divided by L naught minus X. But I'm still satisfied with the way that I did it, you know what I mean? But hey, let's figure out what mass of A is. Let's figure out what mass of B is. Because it just mentally made more sense. You know, later, then you can cancel things out and just know things are going to hella cancel. And so that was the benefit of that. So let's throw in our X value of 10. And so we're going to have 20 divided by 20 minus 10. And that's going to be 2, so we have natural log of 2. And then we're going to multiply by 10 times 2. Oh, and my bad. You know, I'm totally forgetting the square root. So again, this is going to, yeah, this whole thing is squared. You know what I mean? So there you go. And so we have this. So cool. So we have that whole thing squared. And then the square root of that gives us that 11.7. Okay, so now we have velocity as a function. And what do we know velocity is? I guess we can write over here. Velocity is dx dt. You know, we really can't do the chain rule. You know what I mean? Like, what are you going to write? What are you going to be like? Dx, you know what I mean? D McDonald's, you know what I mean? D McDonald's dt. I don't know. I just figure like the chain, you can throw anything in, and I'll come up with a better one than McDonald's. But, you know what I mean? Hey, you know, so, but yeah, because you can, as long as something's changing in the problem, that's an actual function, but yeah, there's nothing changing that's McDonald's. So anyway, so you can't, I don't think you can do chain rule again. I mean, I guess you could. Couldn't you just say, hey, change in X divided by change in velocity again is d velocity dt. You can throw anything in there. It's just you're changing your position, you're changing your velocity, you're changing your velocity, you're changing your time. But change in velocity, change in time, well, that is a parameter. That's cool. It's like, yeah, you're kind of doing the chain rule in reverse. So I didn't expect that to be anything, but change in velocity, change in time, this is the definition of acceleration. So yeah, you could differentiate with oh, that's bizarre. So you could say velocity is dx dv, and then acceleration. But yeah, I don't think that's useful at all. So anyway, so just for this one, we're gonna say, hey, this is dx dt, and now this is the horrible thing, is that we have to oh, and now what is it? See, we need to graph this. Yeah, that's what I wanted to do. So if we have this is velocity as a function of x. And so again, we have meters right here, and we have meters per second right here. So if we get some whatever graph and we find the area underneath it, this is just a good thing to do, is that, okay, the area underneath it is going to have units of meters per second times meters. And just always do that to see if you get something useful, because we don't. We get meters squared per second. You know what I mean? Not very useful. But now let's flip this. Let's take the inverse of this to the negative one, and then our units are seconds divided by meters. Now let's multiply these. So we have seconds divided by meters times meters. Whoa, meters cancel, and we're just left with something that's seconds. You know what I mean? So that's exactly what we're doing with this. We have an equation that's velocity as a function of position. You know what I mean? So that's just what we have. Yeah, velocity is a function of time. We can say that. We can say velocity is dx dt, and here's velocity. But when we do that, when we say dx dt, you know what I mean? We separate variables, but this isn't a constant. We can't just throw dt over here and then integrate and then have an extra t like gravity, and then just change this to x. No, we have an x value over here. So you need to separate variables. Your dx, your deriving variables have to be on the top. So I can't just take this dx downstairs and integrate this. I have to take this and put it under the dx, and then I have to take the dt and bring it upstairs. Okay, and then again, you know, I'm saying velocity is this. So instead of this v term, we're just saying, hey, this is velocity. dx dt is this equation. All right, so let's do it. Let's bring the dt upstairs. So we have dt is equal to dx all divided by the square root of 2gh natural log L naught minus x. All right, heck yeah. And this is two values, you know what I mean? So when we go to integrate, you have two different things here. Anytime you have a natural log and then like a top and bottom, this is the same thing as natural log of L naught minus the natural log of L naught minus x. Cool. And then let's say that, and then you have constant of integration 2gh on both of these. So heck yeah. So then, I mean, it's still going to be in the square root, and it's still kind of a nightmare. But and you can bring this outside the square root. You know what I mean? You can easily bring this outside just to, you know, get it out of your hair. You can't bring it out. I mean, it's a product. I mean, this. So how do you rewrite this? This is the same thing as the square root of 2gh. You know what I mean? Times the square root of natural log L naught minus natural log of L naught minus x. So sometimes visually that is just nicer. And then we have dx divided by it. But now this, it's still square root 2gh, but it is a constant. You know what I mean? So then when we integrate, we can bring it outside of the integral. So now this is still u substitution. We still have a u value down here, and we might as well not waste paper and then just go for it. And so our u value, and you know, I can just see that it's a u substitution. I mean, I don't know. You know what I mean? Maybe it's not. And maybe it's just a lot harder, because what I see here is we're going to have something that's dx divided by u to the negative half. And then we're going to say u is equal to natural log L naught minus natural log L naught minus x. And now we're going to say, hey, what's du? What's du dx? And I have no idea. You know what I mean? What's the derivative of natural log? What's the derivative of what's d I don't know why I can't write natural log. Natural log of x dx. And this is fascinating that I don't know this. I think it should be real easy, or maybe is this the one that gets caught in a loop? I don't think so. Because if I have the integral, remember how integrals work? If I have integral of x to the negative 1, integral of that dx, and this is just 1 divided by x, this gets me natural log integral of this dx, because we have x to the negative 1 plus 1 divided by negative 1 plus 1. And so when we integrate, this goes up. And so you know, we go x to the negative 1. This goes x to the 0 divided by 0. So that's technically what natural log is. It's x to the 0 divided by 0. And then so when we differentiate this, in this way we went up. Now don't we just go back? But I don't know. That's why I think it gets complicated, because I don't think it just goes back the other direction. So now I'm going to take a second and just be like, what's the hell's the derivative of natural log? All right, hell yeah. So just like we have all the integrals that are really useful, you know, just a couple pages, we have all the, and now this is going to give you in its, I don't know, not necessarily more complicated, sometimes the most simplest form, but this says that, and it doesn't give natural log, it's just log e of u, you know what I mean, but that's natural log. So we have the derivative of natural log of x dx is going to equal, or actually natural log of u, that's going to be 1 divided by u du dx. Well, cool. That's exactly what we thought. And I'm glad we went over this, because that just kind of really explains it. It's just like, well, integration goes one way, differentiation goes the other way. And so integration is multiplying these two together. So if that's the case, what's the derivative? You know what I mean? If I have position, if I have meters as a function of time, you know what I mean? This is always like your position as a function of time graph, and it might be an x squared, you know what I mean? Then what is the derivative? The derivative is going to be the change in your y value, is going to be the change in your meters divided by the change in your you're this value. So, I mean, essentially, instead of just multiplying, it's dividing. This divided by that. So we get meters divided by seconds, and that's saying that not the area, but the slope of this line is going to give you miles per hour. So if I know my distance and time graph, you know, and it looks like this, every slope on it is going to give me my velocity. That's my velocity at that point. That's my velocity at that point. And I'm going to do this more because it's just, this needs to get, anytime you're working on a complex problem, it's just like, no, people forget the absolute basics. It's just like, yeah, area under the curve is this times this. That's going to be the units. Differentiation is this divided by that. It doesn't give you the area, but it gives you the slope. Cool. All right, so just from this, hell yeah. So we have du dx. And we just found out that that's going to be, you know, if it's just natural log of x, hell yeah, u is x, and we say u is x, and so du dx is just 1, and then it satisfies. The natural log of x is 1 divided by x times 1, and we just have that. Now for ours, I probably need to get some more paper going, but I bet you we could do it. So this is my full u value. Differentiating it, you can see that this is a constant, so this is just going to go to 0. Now do we have to use like, yeah, you know, even though we have this is u, we're going to say, hey, this is du dx, and you could say this is u prime, you know what I mean, because we looked up in the book, well, if we have natural log of something, hey, look at this, u prime, then now this, so if we have negative natural log of u prime, obviously the negative can come outside of the differentiation, but we have natural log of u prime, and don't forget about that negative though. Then we're going to say, hey, this is u, and then we're going to say, hey, what's du dx? Well, it's just the derivative of, this is a constant, that goes to 0. Negative x goes to negative 1. So now, you know, if we do this, we're basically saying the derivative of natural log of u du, sorry, yeah, what do they say, dx? Natural log of u as a dx, is that what they do? Yeah, dx is equal to 1 divided by u du dx. And then so in our case, this is what we're deriving. 1 divided by u is just 1 divided by u prime, so we got 1 divided by L naught minus x. Cool. So that's this value. We have the derivative of u, so that's going to be negative 1. Cool, negative 1. And we can't forget that we forgot about this negative sign anyway, so we actually have an extra negative. I'm just going to get the hell rid of those. I hate negatives. And so now we did it. So the derivative of this was just 1 divided by L naught minus x. So sweet. So that was pretty simple. And now we need to go back to what we had over here. So here we're integrating dx u to the 1/2. Now is this how you do integration of you know, no, because you need a du. So if we yeah, I did this wrong. So if we do u substitution, this has to be du. You know what I mean? Because then, and let's get some more paper. Alright, hell yeah. So we're back, and you know what I mean, I rewrote the velocity equation. That was velocity as a function of x. Hell yeah, that's dx dt. We separate variables. dt comes up here, this comes downstairs. Hell yeah. And then, you know, we were trying to get du, you know, du is u to the 1/2 because that's the square root. But I forgot that we did a second step. We got this the hell outside of the integration as a constant. So we have square root of tgh outside of the integral, and now we have dx, and then we split this up. This is natural log L naught. Because we have the divided by, it's natural log L naught minus natural log of the downstairs. Sweet. So now we can say that our, now we can do our u substitution. So this is going to be du u to the 1/2, and I think we already said that. We'll do it right here. So our u is natural log L naught minus natural log L naught minus x, and du dx is going to be, this is going to be 0, and again, let's do it. We have the minus, you know what I mean? Can't forget that. Now we're going to have 1 divided by u, which is L naught minus x, so we have that term, and then we have the du part. You know what I mean? So, because remember, this comes from derivative of natural log of u dx is equal to 1 over u du. And then so for our problem, so for our problem, this is u, because we have the natural log of u, and then so we have to figure out what du dx is, and that's what we're doing right now. Oh, holy hell! No. I'm sorry. This starts off this equation. So yeah, if this is u, if u is just L naught minus x, du is just -1. Cool. And then so here's the structure of the u substitution for natural log. So if we say natural log of u, which is that, is equal to 1 divided by u, so sweet. So we already have this. So it's derivative of natural log of u dx is equal to 1 divided by u. That's L naught minus x times du, which is -1. But again, I'm just treating like this as this negative as outside of the differentiation. You know what I mean? So that's what I'm doing. And then so this whole thing becomes negative. And these cancel. And then so hell yeah. So we have... so we just did it. We just did what du was. And then, yeah, we were kind of saying this is like a... this u substitution was like u prime. You know what I mean? Just to not get confused with this u... you know what I mean? Hey, yeah, okay, so we have this u. This du is different. Oh, this is tripping me out. So if this was our u inside, maybe it's not. No, yeah, it was. Okay, so if this was our u inside, we found the derivative of this u. And to do that, we had to say that this was 0, and then we had a second u. We had to say this was natural log of u prime. I don't know any way to make this just like not a headache. But we still, but what we found was the derivative. We did find this du. You know what I mean? So we said, hey, this is u, and then we found the du part. So let's write it again. Du is going to be positive 1 divided by L naught minus x. So hell yeah. So let's do that. Okay, sweet. Man, this shouldn't be too complicated, but yeah. Oh, but wait a second. I forget how u substitutions work. Oh yeah. No duh. So we had to say, let's come over here. So we have du dx, and obviously this u is this function, and so you could write it like this. You could say d of natural log of L naught minus natural log of L naught minus x. There's a couple ways to write derivatives that just kind of make sense. Now we're differentiating this with respect to x. Now we get du dx. This is a full term, you know what I mean? Nothing changes on this side, but we evaluated this. And now we say this is equal to 1 divided by L naught minus x. So I'm mistaken by not saying this is du dx. This is the derivative of u. And again, you know what I mean? You can also write these as like, you know, because it's sometimes useful to be like, hey, y as a function of x is equal to x, and I want to know the derivative of y of x dx. You know what I mean? That makes sense. Now it's just 1. Instead of being like, well, dy dx, it just seems like nonsensical. It's like, I don't see what the hell you're talking about, but it's like the derivative of that function. And so that's what we're doing. It's like, hey, and at the end of the day, it doesn't really, well, I guess it doesn't really matter, but usually your function says, hey, y is on one side and then all the other stuff is on the other. So what we're saying is like, hey, if we change x by 1, we'll just do this one. If this goes from 0 to 1, so starts at 0, and then the next value is 1, how did y change? Well, y started at 0 and then went up to 1. So the change in y was 1, the change in x was 1, so our derivative, our slope is 1. Cool. Okay, holy hell. I mean, I think this is valuable. It's valuable to me, you know what I mean? And I think it's valuable to other people where you're just like, when someone doesn't just have like, I just can't do it, you know what I mean? So you can probably see it 10 times faster than I can. But now this is the tricky, I always thought this is the tricky part. It's just like, well, you had this as u, we did that, and then we needed to find du. We'll look at what we need. Just think of it as an equation. You said this was u, and then you have to find du. You know, if this is u, and if this was u of x, you know what I mean, then du of x is dx. You know, you have to differentiate. Du means du of x dx, and so then you get something like this, but now you just have to solve for dx, because that's what you're replacing. Maybe what I said before is just like, well, it kind of gets headachy. But you did du dx, and we're solving for dx, so dx has got to go upstairs, and all this crap's got to go downstairs. So now we're going to have something like this. I guess we'll just do it over here. So dx goes over here, and this is going to be du divided by 1 divided by L naught minus x. So 1 divided by L naught minus x is the same thing as multiplying by the inverse. So that would be L naught minus x divided by 1. This is the same thing, and obviously that's the way to do it. And so we're going to have dx is L naught minus x du. So now when we go place this dx term into there, that is going to, it's going to give us this. And is that going to make sense? Well, let's try it. So we're going to have the square root, the integral dt on that side. And then once we integrate this just becomes a constant t. So basically we're going to get t as a huge function of x. Cool, and that's kind of what we want. We want time as a function of position, I guess. Oh man, I feel like we're so close. So we have, so cool. And then once we get it into this form, I forget, we have to solve it in this form. So this obviously is u to the negative 1/2 du. And then so when we integrate this, we're going to get u to the negative 1/2 plus 1 divided by negative 1/2 plus 1 plus a constant. Cool. And so that's gonna be u to the 1/2, and this is gonna be 1/2. So we have 1/2, and yep, you know what I mean, because whatever this exponent becomes is what we multiply by. You know what I mean? So if it's t squared and we're integrating dt, it goes t cubed and then 1/3 divided by it. So if we go, whoa. So wait, no. So I caught my error. Dividing by 1/2. Thank goodness I caught my error. Holy hell. So now we'll have, this will be u. Once we integrate, it'll be u to the 1/2, and then we divide by 1/2, which is the same thing as multiplying by 2. So we're going to have 2u to the 1/2 plus a constant. Hell yeah. So then all this just becomes, but I guess where I'm confused about is right here. When we throw this into dx, we're going to have this extra term right here, and this I think is just part of the constant of it goes outside the integral, So we're just going to have this L naught minus x outside, and then we do this, integrate this, and we get 2u to the 1/2, which is 2 square root of u, and then our u is this term right here. So Haley, let's try it out. So we're integrating this side, and we get t. So we get t is equal to, now I'm gonna do this one first. I guess I don't have to. So we're gonna do the square root of 2gh L naught minus x. And then we're going to have times 2. And then we're going to have the square root of u. So we have natural log L naught minus natural log of L naught minus x. And I feel like pretty confident, but not terribly. You know what I mean? So I have no idea if this is actually right. But the cool thing is we already did this in Excel, and we got everything. Just within seconds, we did this in Excel. And so in Excel, we had a value of time as a function of position. So let's just do it right now. If this is true, we're going to throw in 10, and that's going to give me my time. And I'm going to take a printout at Excel and just see if it's the same. If it's the same, I'm going to be like, oh, hell yeah, my skills are really good of not making mistakes today. But anyway, so we have the square root of 2 times 10 times 10. And see how just setting up an initial problem that's just hella simple just makes life easy. Sometimes you don't want to make it too simple where you might have an error, but it kind of cancels out or something. That definitely happens. All right, so this is 20 minus 10, and then times 2, and then we have the square root of natural log. And this is still just the natural log of L naught minus x. So we could do that. So this is the natural log of 20 divided by 20 minus 10 is 10. So let's just do 10. And I think I'm pretty satisfied with that. Okay, and now we have a time value, and damn, it did not like that. It's not going to take 235 seconds. So now I want to know, like, what's driving this that's so messed up. Bummer, man. The other thing is, I'm just trying to think of why this didn't work out. This is going to be time as a function of position. Time's on top. We did this divided by. So, yeah, obviously, this all looks good to me. 2 times 10 square root. 20 minus 10 times 2. Natural log of. Yeah, let's redo this one though. So we have the square root of natural log of 20 minus natural log of 20 minus 10. Okay, so that's going to be 0.8. And if we go back up here and just, we just said that's the natural log of 20 minus 10. Is that right? Or no, 20 divided by. Oh, see, yeah, my equation's wrong. My bad. I think my equation. I instead of dividing, I think I did minus. So yeah. But yes, the square root of that. Okay. So I think I caught my error. I think right here. Holy hell! No, I didn't. I divided. So if we had this, sorry about that. If we have this, we multiply by 2, multiply by 10. Yeah, this thing just goes up, times the square root of 2 times 100. Yeah, and unless we take the square root of the whole thing, I just don't see it. So let me check my Excel, and then I'm going to try to catch my errors, because obviously there's something wrong in my integration. Alright, hell yeah. So we're back, and disregard everything about this integration. I think once the du didn't work out and we had this little extra term, there's just no way. And if you with integrals, it's just like you never know if they're going to be easy or confusing as hell. But yeah, integrals are tough. Differentiation, you can pretty much differentiate anything. But when you take integrals, so this is what we have. We have you know what I mean? We have 1 divided by, well, did we write it a couple times? Yeah, I mean, we basically have this. So we have, oh, you know what? Oh, so maybe I'm going to give this another chance. But no, like, I even have this wrong. Like, holy hell. Like, this has to be 1 divided by 2gh. And I think this is absolutely, well, there's a chance I don't think so, because when we throw it into the integral calculator, if we integrate this, it's an error function, which is a thing. It's a probability between negative infinity and infinity that's just going to say, hey, like, I think it's just going to be like between -1 and positive. That's the general gist of the error function, but I don't get it. I don't even know how to put this in my calculator. So, and there's just no way. I don't know enough about integration, but I can guarantee that just dividing this by 1/2. Well, let's try it. So we have this is going to be natural log of 20 minus natural log of 10, and then we have the square root of that, and then we're going to multiply by 2, multiply by 10, and then divide by the square root of this. This is 200. 10 times 10 times 2. Divide by the square root of 200, and we get a time of 1.77. Now maybe I did it right, and then just, the integral calculators online, just, I don't know. You know what I mean? I don't know enough about integration, but I just don't think, but at least I caught my error. This is downstairs. There's no way you can just take that upstairs, you know what I mean? So that's got to be 1 divided by. And so we have this in Excel, and we just did it, you know what I mean? So we can say at 10 meters, this is the meters, and then we can say this is the time. It took 1.9 seconds. So this is not legit, you know what I mean? So this is the actual. These don't lie. These integral calculators, and then I did it in Wolfram Alpha. You get the same thing. There's just you know what I mean, square root of pi divided by 2. This one's a little bit different. I think they just mix some stuff around. Yeah. But cool. So those are the 2 different types. Okay, but you know what I mean, regardless of that, this is just really showing you. This kind of doubles down on like what the hell did we do? We used the F equals ma thing. We found the force net, and then you just divide by the mass total. That was ma plus mb. But then, and that was a function of x. But sure, you get an acceleration at every point, and then you just choose a small change in time. Acceleration is you're going to be changing velocity during that small change in time, and again we get it. So just the fact that we have this is invaluable resource, especially when the math gets too complicated. But we're going to do one thing. So we know that this is the velocity, and so again we have velocity as a function of position x. And this is in meters, and this is in meters per second. You know what I mean? And the area under the curve would be meters squared per second, which makes no sense. So we're going to invert this. So we're going to just take this velocity. We're going to go 1 divided by velocity. You know what I mean? Is just 1 divided by this. And if we graph this in our calculator, we'll have seconds divided by meters, and we'll have an equation for that. And then the area under the curve is going to be the time. You know what I mean? At that value of x. So let's do this. You know what I mean? It'd be kind of cool. And this is kind of what we're going to finish with. But this is a legit thing to do. So we have 2 times 10 times 10. This is gravity times h. And then natural log of 20 minus 20 minus 10. Or no. We're going to throw an x right here. Yeah, duh. So this still is a function of x. And we divided everything by 1. Let me just double check. We got the square root. Oh, I guess it doesn't really matter. Once we have the square root, we're set. Cool. So now this is going to give us, we still want x to be 0 to 10. So yeah, I'm just going to go zoom 6 because that goes to 10. And now we're gonna go from x is 0 to 12. And then the y is going to be 0 to 0.2. Graph that. So here's our graph, just kind of visually a little bit better. And what we're going to do, and I guess, damn, this shoots up to infinity, doesn't it? Because what we want to do is actually, well, bear with me. So we're going to go this to be 1 and then see where it is. Oh, weird. So this graph doesn't even start. So we're going to trace it out. We're going to trace it out, and it only starts at x is equal to 1. Yeah, because of the natural log. So that's a bummer. This is just going to give us... oh, well, no, what the hell did we say? Oh, well, I was trying to say, hey, the area under this curve... the area under this curve would give us the time value at x, equals 10. But this thing don't start until x is equal 1. You know what I mean? So let's see on our graph, like how much time passes when we get to 1 meter. Quite a bit. Holy Toledo. So this is 10 meters. And yeah, I only have the first page. So let me print off the next page, because I'm just curious if this is even going to work, because we do have an integration calculator. And so let's just do the lower limit, pretty close to 1. And then the upper limit we'll just set as 10. And it's going to give us an area under the curve, and hell yeah, that's going to give us, that says the time is 0.556 seconds. But yeah, that's why this equation's a mess, because you can't integrate from 0. You know what I mean? So you actually can't find you can't integrate from x is equal to 0 to x is equal to 10 for our case. So I had to integrate from 1 to 10, but for that first meter, you can see in Excel that tons of time is going to go by. And so what we're shooting for is that we know that the total time is going to be, what, 1.9 seconds? 1.9 seconds, and we just said this integral was 0.5, so 0.555, there's 3 5, sorry about that, 6.629 seconds. So now we're going to say, hey, at Excel, at a distance of 1 meter, you know what I mean, when we get to 1 meter, we should have the difference. So that's going to be 1.9 minus 0.556629. And in Excel, at x is equal to 1 meter, we should have a time value of 1.34 seconds. So let me pull that off and print that out. Alright, hell yeah. So we're back, and yeah, I love my series because I just feel like I can find errors really well. So you know what I mean, because even just doing this Excel shouldn't lie. You know what I mean? And this equation shouldn't lie, and I was getting the wrong answer. So yeah, and I went back to this equation, and whoa, I just make mistakes. This says natural log of 20 minus, you know what I mean? So obviously it's divided by, and so now we're going to graph that, and so this should change our value. Oh, okay. So yeah, now we're good to go. Oh, so yeah, so it's so fascinating. I thought as I had it, we couldn't go to 0. We couldn't integrate from 0. But now we're just good to go. So even though like the integration of this is an error function, or some kind of crazy probability thing in advanced math, you can just graph it in your calculator. So that's what we were hoping to do. We're going to get this y to just a little bit. So it's still, so let's trace it out. We're going to go value 1, and then we'll just trace it and see how far it goes. You know what I mean? Hey, we can't get up to 0, but we can at least start here. So now let's try this integration out. So here's our lower limit, and then our upper limit is whoa. So let's try it again. So we have a lower limit and upper limit is 10. And heck yeah, so it's going to integrate that and then give us a time value. And this says our time is going to be 1.716, and I'd say that's pretty close. We just this cannot integrate, just that little piece. So let's try to do this. We're going to go 10, and we'll try to get this y to be 1. And see if we can capture it. Well, let's go y max is 1.5. And there we go. So maybe we can capture it just a little bit better. So we're going to go integrate. Well, we need to go to about here, value 0.1. And so we're going to integrate from basically 0 Yeah, so right here, so it crosses the x, and then it's undefined over here. So right here, this is going to be our lower limit, and then our upper limit is 10. And so we're just going to, damn it, not graph it. So the lower limit, and then upper limit 10, enter. Oh, see, it's too close. It's too close where it'll give you a bad value. So we're going to have to just... So our lower limit can't be here, but maybe... Yeah, and that's too bad. Because, and then our upper limit... I mean, just right there. Well, oh, yeah, so we're good. Yeah, so, yeah, well, let's go back to this. So we got our lower limit. And then our upper limit. We'll just scan to it. No, it's taking forever. I don't like the fact that these TI-80 calculators are a little bit slow. You know what I mean? Like when you're trying to do this type of stuff. Oh, and I get why I didn't like 10, because I can't even register 10. Because I have here. So we're just going to go to 10.1. So we're... Oh, whoa. Damn it. What did that do? So we got negative 2x max of 10.1. There we go. So now hopefully we can capture this. So we're going to get our integration. Well, get to a value of 0.1. Sorry about this. And so 7. So our lower limit can be right here. Sweet. Hey, so now we're pretty good. And then upper limit's 10. Oh, it didn't. Oh, it did like it this time. Sweet. So, and now we have 1.877 seconds, and that's 1.9, and that's what we have in Excel. So, hell yeah. So we were able, and so, you know, I mean, what did we do? We took our velocity function, and then velocity was a function of position. The area under that curve is something ridiculous. But if we go 1 divided by velocity, that's going to be that's seconds divided by meters, and then we multiply by meters, and we get the value. The area under the curve is the time. So I just wanted to show you that, and you can always just use a calculator to integrate it. And a calculator is basically doing the same thing that you would set up in this. You're finding those values at all those like changes in little slices, and then you're adding them up. You know, it's kind of like the Newton method, or whatever. But anyway, so yeah, so that's it. So I think I'm done with this one. And it just, like, the heart of this was like, hell yeah, find your acceleration equation as a function of x, and then just change your time just by a little bit. You can do, and then you don't have to do any integrations, no differentiations, but mainly those complex integrations, because you got to go from acceleration to velocity as a function of position, and then velocity as a function of time. And man, I guess... You know, going from velocity as a function of time, we struck out on that one. It was high-level math. But since we just have this Excel, we can find everything that we wanted to about this problem. And so, man, this was a long one. But I appreciate, you know what I mean, yeah, I appreciate anyone who's watching this. That's sweet. I kind of more of a narcissistic. I'm gonna pat myself on the back first. So hell yeah, yeah. I'm just happy that I did this. You know what I mean? Because I don't think people do it, and I think there is a value in this where you're just like, whoa, it looks like you struggled through that. Well, yeah, no duh. You know what I mean? Because I chose a problem I don't know much about. You know what I mean? And we sat through it, and then we learned. You know what I mean? And from my perspective, hell yeah, I'm gonna go over everything. And a lot of this stuff I've done a little bit. You know, the integration part, we got it. But definitely integration sucks because you just don't even know if you can do it. And then you get... So anytime you get like a complex integration, throw it into Wolfram Alpha, or definitely support this channel. You know what I mean? This integral calculator, this guy you can donate, and does a really good job for just really clean and crisp of calculating integrals. And they're like 100% right all the time. I don't know how the integral calculator works, but it's pretty sweet. Okay, so I'm done with this one. So thanks for joining me, and guess what? That's a video.